Remember, there's music on Twitch, all you YouTubers, just for the intros. I had Serial running overnight, and I guess it caused massive lag on the webcam. It probably was just pumping data through the USB 3 hub that I have sitting over here. That's how this whole setup works right now, is USB 3 hubs. We've got USB 3 running directly out of the rack over there. That goes to all of the cameras around. And then I have USB 3 coming out to a hub over here, and that does the face cam. Until I can do NDI. I think I ordered a Raspberry Pi 3 from SparkFun, but they haven't gotten, or Raspberry Pi 5 from SparkFun, but they haven't gotten in yet. I need two NDI nodes, one on each end of the shop, so that I can have one over by the 3D printer that'll have two cameras on it. It'll have a 3D printer cam and a board cam. And then I'll have another one going out to my desk where it'll do the video from gaming, and as well as my face cam during gaming. And then I can have, maybe this one could remain untouched. It doesn't have to be on NDI. That way I don't have to slink cables all over the place. But this is something that Fletchling Goodman has been pushing for, and I should probably go to Sammy board when I do that. It's not Sammy board. What is it called? Sammy? It's just called Sammy? Is that it? Sandwich? Let me put some traces down here. Not a lot of activity in the chat over the break, but we don't really expect there to be. I mean, I could do this. Nah, I'm not gonna do that. We need to do the correction on the other board as well. All right, so we've got all our corrections in on this one. P6 is corrected. This one is ostensibly ready to order again if I need to. So I'm going to save that, and we're going to go to the chord VCO. Now, we haven't started yet. I'll just put up a start soon on here, because this isn't what we're doing today. What we're doing today is going to be a little bit of MS Paint and a little bit of Salon-Key filter. We gotta read about some Salon-Key filter. Now, this is the chord VCO. I need to go all the way back to the schematic, and I need to update all the stuff. That would be in library, and then I click on this, and I go update design from library, blah, blah, blahs, and it says, oh my God, something happened, and then we fail the design rule check, because we are a bunch of failures. That's just our legacy. Let's go to the top layer. Let's just take a look at that. All right, so we need some traces on that. So I'll go to some traces, and then I will add 0.3, and because it's a different instance, it doesn't remember, 0.3 millimeter. These don't need to be huge. All they're doing is tying the grounds together. They're already tied together, the grounds and the voltages. That one's kind of off. Let's do that again. It just ties them together. It's not really a necessary step. And we're facing the right direction, so the stripe on negative. Stripe should be pin 1. Yeah, I guess it is pin 1. Okay, pin 1 and 2. And then this is what changes, and it blew up some stuff. So let's go to our, well, the top layer. Why is that? I guess it drew that for me on the top layer. Huh. Let's go to the standard bottom layer. Let's see. This is Big John, by the way. It's a Big John mix from 14 years ago. If I had a baby when he did this mix out of a 14-year-old, let's see. Preset bottom, and then we're not quite looking at it the right way. Our silk screen is the wrong way, so if we flip it, that flips all the layers around, and so the silk screen is up top, and things look good again. So delete that, delete this message, delete that message, and then we're going to put down a 0.3. We're already primed for 0.3. We are on the bottom layer up here, and so I can go from here, and we're doing curves. Of course, I don't have my curve thing programmed in correctly. Let's actually go the other way. Let's go from the other direction. So we're going from here. We'll just try to get that as flat as possible. Bring that over here. And we don't have anything to do with this because we can't get over there. Although we do have a trace on the other side of the board, which might be annoying for me if you know, well, I wish I'd gotten the part correct to begin with. Let's look at the top and the bottom at the same time, and let me get the vias distributed. So I can redistribute some of these vias in order to give us better ground coverage. It just gives us a semblance of shielding when we run signals around our board. It's not totally vital, but since vias are free, I might as well use some of them. One right there. It's more of like a feel thing for me, at least, doing these. It's like I've worked with RF, and I've not really ever had troubling, spurious signals running around my boards, because we don't do stuff that's fast enough to justify any kind of RF filtering. We really don't. I mean, this is like audio range stuff, so we're not really going to see a whole lot going on when push comes to shove. All right, so we did the switch. We did the text, the cursed text. Oh, it's still a little bit bad, though. That needs just a little bit of room to breathe, where it's not going to get covered over by something. We did the power thing has been flipped so that the pin 1 with the stripe on it is in fact negative, V negative. D1 and D2 are in a good place. What was our other correction? Our other correction was the pin swap, and I did that last time. Our ground is a little bit crowded over here, but it does get good ground. And this one gets ground and a loop around. But yeah, that was just a matter of running it slightly differently. Instead, it went to here before, but I think this is okay. This V is a little bit close in there. It doesn't have anywhere else to go. How is he going to see without his glasses? Can we fit it up here? Negative. Oh, actually we can. I'd kind of rather it be there, because this gets ground from here and here. So it's better that it gets a nice solid big ground plane nearby. I don't think that's really going to affect much, but as long as that fits in there, it should be okay. Positive and negative. Yeah, everything's looking good here. We may have to take this board and build it up, which means I have to figure out where the hell I'm getting a couple more potentiometers. Update that. Not new group. Properties. So this one is edited, and it's 3:22 now. How time passes. I don't think I'm going to do revs on this. I'm not going to mark that. Let's go to the other one and make sure that we've got the date on there. Boom, 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 boom. Timeless music. Timeless, timeless. Although it does have a runtime. I kind of need like a dot on this thing to mark pin 1. I guess we're okay without it. I thought that was the silkscreen marking, but apparently none of that comes through. Let me put down some text, I guess. We want to go to preset bottom. Look at that bottom. Preset top. That turns everything off. Preset bottom, there we go. Okay, so get this out of here. And then I'm going to place a dot down here. I'm going to go to the bottom layer, which is what we're editing. Actually, wait, we're bottom silkscreen. There we go. And then text, we want document, draw text. Actually, if I just draw a dot, because I don't know, I don't know what the symbol is for the dot, and I don't have a keypad, so I can't do the alt numbers. Let's do that. Good enough. And just move it like right there, where it'll show up nicely. Good, good. Let's look at the top layer too. Looks like I can sneak a via in there. Just like that. It's a little close. It's a little close to the pins, but the solder mask should cover it. That just gives us a little bit more coverage. Nope, won't let me do that. I guess it's too close to everybody. Oops, no, let's redo that. There we go. We don't necessarily need all this shielding. It's just nice to have. Actually, I want to move this over here. Oh, no, I can't. What's over here that I can't get near? Let me over here. What the heck? Why are you so ornery? Why you gotta treat me like that? All right, fine, we'll just put it right there. That'll be okay. I'm not being a total crazy person about grounding. Although we should have one over here. There we go. That just gives this whole plane a little bit more to draw upon. Oh, same with here. There you go. I don't think I need to go that crazy with vias, but I'll put a couple more in here just because. Alien Dance. Why didn't that show up on any of my stuff? What is going on here? I'm going to refresh this one. I've been having troubles. I think this computer just desperately needs a restart. I think some of the limitations that I had going on it before with running all, all the software that I've got running and all the programs that I've got running and all the windows that I have running, and then having it have a sudden hard drive space issue probably set it into like a cautious mode that makes none of my stuff update properly. Like Wayne Johnson said something, which is great of him to do. I love having people actually chatting, but for some reason, it's not updating properly. Refresh. That didn't do anything. Oh, there it goes. Click the button like 5 times. Let's do this one, and then we'll do... Oh yeah, that's right. This is the one with this pervasive flute that goes for like 2 hours. Where's chat? I don't like the flute part. All right. I'm going to fast forward past this part, actually. That's better. What up, kindergarten kitten? And yet, it still doesn't show up on my freaking feet. What is up with this? Where are these messages? Why aren't they showing up? Like, Social Streamblade has been really good, but for some reason it's seems to be slacking lately. And it might just be my Chrome doing weird stuff. 1, 2, 3. Oh, now you show up, now that it's one of my messages. And then we'll test out 1, 2, 3. There it is. I don't get any weird credentials for being the streamer on YouTube, huh? I guess it highlights differently. Okay, there we go. Annoying, but we're here now. How's everybody doing? How's your Friday shaping up? I got a lot of sleep last night. I went to bed at like 1 and then got up at like 9. I did laundry in the middle of the night, but and not all my laundry. My shirts are still drying, which is why I'm in one of these ones that doesn't fully cover my fucking belly. I shouldn't curse this early into stream. I'm sorry. I'm so sorry. I'm so sorry, Pepsi Company, that you can't run your ads. I'm so sorry. All right, some of the window dreck that we can get rid of here. Just anything we're not using, get rid of it. Ucho, we keep. This is Hagiwo, we keep. This one, I don't know why that's even open. That's the original Hagiwo. Here's Hagiwo's YouTube channel, pretty cool. I don't know how he's making these panels. Maybe he's got a printer or something. And then the Seed Studio, and then we don't need this one. There we go. So many fewer windows. Let's get rid of some of the programming windows too. Oh yeah, I gotta change the date on this one, hold on. That was the last thing, 3/22. Apply, okay, there we go. Only way to tell the two boards apart is by that marking. Well, and the fact that it works. A long time no see, kindergarten kitten. Okay, let's see. What else? Getting rid of this window. Oh yeah, back, what, 10 years ago when this mix was made? My buddy Big John... Oh, that's the face focus. Oh, crap. Let's just do that again. Back when my buddy Big John, PHL, made this mix, he got a mixer that had like a little fade effect on it, and he used it a lot. So expect things to go right and left audio quite a bit. All right, so this is the one we're working on. We need this one. VCO only is where we're going to be working in. And then, which one are we? This one is the rewrite that I abandoned. I'm going to close that one. It's our test program that we're going to be operating in. Because that way we can do more stuff. We can slowly walk through it all the modulation and encoding and stuff, which I suspect is going to get kind of complicated. I really need to get my audio off of these VSTs. I need it to be physical, a physical piece of hardware. Would have been cool to get like rack hardware and have like the audio rack that controls everything, but that's really expensive. Physical hardware is not cheap, and I could build something. I could always build something. That's always an option. You got to look for sales from church audio in order to find good audio gear, because decent, like low-level streamer like me audio gear, like absolutely go get church audio, because churches spend a lot of money on their audio, and then they'll re-up all their stuff when it gets old. So even though it's still perfectly effective for broadcasting, you just get some old styled stuff. And I wanted to do Aviom, I wanted to do networked audio, but apparently there's much, much easier ways to do networked audio these days than Aviom. Aviom is just a company that I worked for, but I could have gotten some of their ANET stuff and had 16 channels of mono audio that I could run throughout the shop, and I could have input and output nodes everywhere. But apparently there's much better solutions for that sort of thing nowadays. Turn the scope on. That's going to take a full minute. I just hit the power button. Believe it or not, I just hit the power button. As time goes on, it gets a little faster in booting, but it still takes a full 60 seconds. It took like 3 minutes for the thing to boot up the first time. I don't know what it's doing. It's not exactly compiling shaders. But it's basically an Android tablet in a frock. You add these buttons and stuff to an Android tablet. It's a very easy thing to do engineering-wise. Still waiting. Anytime you're ready now. It's cool. We don't have a lot to do. You could just take your time booting. Oh, whoop. Almost did it. Wait, it made a clicking noise. There it is. Now we can use our scope. Yeah, it's kind of a walk away and get a cup of coffee kind of affair. You gotta go get a cup of coffee and come back and all's well. I'm gonna free up some memory on the computer. I never thought I'd have to do this. Actually, wait, let's check first. So, hold on. System interrupts? Hello? I think that's because I had the serial port running overnight. 50%. Jeez. Fusion's taking up so much less. OBS is eating most of the memory. 71% of my memory is in utilization right now. Chrome is obviously the big offender, but that grows to the size of its fish tank. All right, I'm going to free this computer of Fusion 360 because we're not going to need it very much today. And I don't know when I'll order PCBs because we still have to test the other, the cord VCO. We're not even ready to do that yet. Yeah, this is a moderately spec'd out system. It's mainly the stream computer. It's for stream and work. So what am I going to do? Program Arduinos with, 16 gigabytes, 18 gigabytes of RAM? Then finish the jobs. Jeez. I don't need to hold your hand. You're a goddamn CAD program. Let's go. Are we ready? There we go. Okay. Computer's like, gets a little breathing room. No, I don't have a circuit printer. I don't think there's much utilization to a circuit printer. I don't really think they're necessary this day and age. You don't need one. You can go to any of the circuit board manufacturers, and as long as you keep your board within 100 by 100 millimeters, which is most boards that we ever make, you get $5 a PCB. It's a trivial expense. And they're professional boards. So we get people coming in here often asking me about whether or not, hey, I'm just getting into electronics. Should I get a CNC machine so that I can make my own boards at home? I get that question a lot, and it's no, absolutely not. You should not. You shouldn't even pay money for your CAD program when you're starting out. Your expenses are going to pile up, like getting soldering irons and parts and stuff like that. Parts are especially one of those things where if you've got a big shop full of parts, everything seems cheap, but when you're just starting out, you've got to buy all those parts, and you got to buy more than you need of everything, and then it becomes pretty expensive. It's like death by 1,000 cuts. Every order is $40, $50, and you got to make 5 or 10 orders, that sucks. That's part of building up a shop. And so having something like a circuit board printer and all the chemicals and supplies that you need to do that's way out of scope for somebody who's even a moderate electronics hobbyist. Even a beginner electronics professional does not need that stuff. You go to Seed Studio, you go to JLPCB, you go to any of a number of places that have bought a big industrial printing machine and have all of the scripts that they run to just take orders in, panelize everything, print, and then throw the boards in a shipping container on its way back to you. $5 for 5 PCBs. You do not need any printing material at all, like supplies at all. Just have the building stuff in order to build your circuit boards. That's it. Myself, as a moderate professional, I could have spent the past 8 months, instead of putting together a synthesizer, I could have put together a precision CNC in order to build circuit boards. It's not worth it. It's just not worth it. I get better stuff from Seed Studio. The DIY boards that I've made at one of the big 3-letter agencies were of a quality that was far inferior to what I would just get sending off for a circuit board. So a shit ton of stuff, yet I don't have enough. Yeah, it always takes new parts to do everything you want to do. But save yourself the trouble of pining after a circuit board printing machine of any type of sort, because that solution has been solved. So that problem has been solved tenfold. In fact, it's been solved so incredibly well that it's changed the development process for the rest of us. And that's a weird place to be, but that's where we are. It's a very strange place to be. I was talking to Uo Slab about that yesterday. These are tools that I never use. These pliers over here, these big crimping and stripping devices. But as soon as I let go of them, I'll need them. What to do about that? Try to lay them flat in here. This is an overloaded drawer. Let's see. This is a funky song. I do need to clean up around here a little bit. We need to refocus and look at this milling machine. Take a good close look at it to see if it's doing its job. Actually, what I need to do is pull it apart down to its bones so that we can oil everything and adjust everything properly. This is the Ertlurker block. Let's see, we got a camera over there. Got weird Ethernet cables over here. All kinds of wires all over the place. One of my T-handles is out of place over here. extra audio cables from Julian was here. I gotta get Julian back in here, but I need to make progress on this stuff first. Whoa. He has some one-stream projects and stuff too. Hey, Pyro. Good seeing you this early. Yeah, he's got some like basic stuff that he would like to work on with me, like a very simple panel for his synthesizer. So many things that I would like to have the time to work on. I just don't these days. But this is an important one, getting this VCO done, because we've got circuit boards and we're doing all kinds of good stuff. I'm doing good. I got a lot of sleep last night. Yeah, happy Friday, everybody. Happy Friday. Let's see, we're still on this setup. Still got the O-scope going. We're going to try to do as much physical stuff as possible. We're going to try to punch numbers into the actual microcontroller and test stuff as we go, because that's more interesting than just simply doing code all day. But we do need to get through a significant amount of this code because it's a beast. Carrie, no. I went over to the Omnipod. I switched to the Omnipod. And the Omnipod is well, it looks a lot like this. These are disposable insulin pumps. And so I have one of these on my body. It's got an adhesive patch under it. And my cell phone is coordinating with my constant glucose monitor and just taking over the task of being diabetic for me. It's expensive. It's expensive. I've got coverage of this stuff, but boy howdy, if I had to pay out of pocket for this stuff, I would be dead. But having this stuff, and also the fact that I'm throwing away an entire piece of like expensive, well, $35 worth of electronics, but it's a nice microcontroller. But I'm throwing it away every single time. Every 2 or 3 days, I'm throwing one of these away, which is kind of crazy. I don't know if I like that, but that's just, it's what it's. And $35 worth of electronics, this thing costs like $100, so it's intense. It's like Burning Man, fucking intense. Depending on how much I eat, yes, it is 2 or 3 days. That's what it is. It's supposed to be 2 days. They only put 300 units of insulin in there. And I use a lot of insulin, don't get me wrong, but 200 units, like they could easily make it 300. Yeah, that's the cost of doing business as a diabetic, sorry to say. Imagine spending $400 per bottle for 8 bottles of insulin every 3 months. So yeah, a couple of revisions done on this board that we'd have to do ahead of time. I have one component on this board. Where is that? It's right there. No, it doesn't just suck. It's actually fucking dangerous is what it is. Yeah. So this one's all updated. I don't know where they're going to put their little number. They have to put this little number on the board. They could fit it anywhere else. This one's pretty nice. It turned out nicely. I may order all the new ones in yellow. I may order them all in yellow. Just taking a good look at it. This is my voltage controlled oscillator, VCO, and it's Hagiwo and mutable designs. Even though mutable designs they're fairly common, commonly done designs. Although mutable does, I don't know if that's a signature of mutable, but they do this -10 volt like injection on their amps in order to make the external signals into 0 to 3.3 volts and then limit them there. I don't know if that's necessarily a mutable signature, but I'm giving mutable credit for it because that's where I got it from. And Hagiwo made the Chord VCO, and we're gonna, at some point have to figure out how that works. But right now, we're going to have to figure out how PWM to audio through a Sallen-Key low-pass filter functions. What is this song? This is a good song. It does not tell me what song it is, because it's so old. Oh well. Did I correct the C and the R flip up on the other board? I don't know if I did. If I didn't, that's fine. I'm not too broken up about it. I think I did. I think I did reverse them. It was on the other board. I had a C and an R mixed up, but that's not that big of a deal. Why is that flute back? No, wait, that's a different one, but it's just annoying. It's obnoxious. It's got this sour note in it that I don't like. Oh my God, I'm fast forwarding beyond it. Oh, the song below it was pretty good. I just don't want the front thing. Okay, it's gone. It's gone. It's finally gone. I'm free. Yeah, we're gonna have to do a little bit of math today, and that's gonna require me to make a lot of letters on the with the mouse. As much as I don't like doing that, I do have a drawing tablet. I could plug in the drawing tablet and write down equations that way, but I really seriously don't want to. I'm deluding myself right now into thinking that we're not going to do that much equation work. We probably are. We need to read through a little bit of how the code works and figure out exactly what it's doing. Otherwise, how do I make the chord VCO? There's no way. What else do I got going on? I guess I'm just here with the dog right now. My garage motion alert doesn't work because I need to get up on a ladder and replace the battery. It is cold here. Welcome to the Northeast, where it is again 0 degrees Celsius. Steam Deck or Stream Deck? Stream Deck does me a lot of good. I need to figure out one last thing with this thing. Well, I need to reorganize this one. I have the XL, but the XL does not work with the USB hub that I have. I plug it into the USB hub and it just doesn't boot up. I don't know what it is. I don't know what the problem is. Too much screen, too much bandwidth? I don't know. But if I can get that working, I also need a button that'll rearrange my windows to where I like them to be, because that would really help me set up stream. There's a lot of juggling of windows that I have to do. That's why I want this view, so you guys can see how much fucking information I have sitting in front of me during these intros. I've got this, but this doesn't give me system messages. I need this open in order to run this, and then I have a utrub window over there so that I can moderate utrub. I have a Twitch window that's separate that'll moderate Twitch and give me stats on where my actual viewers are. 2 or 3 days. Yeah, I already got that comment. Okay. Just making sure that I'm keeping up. No, it's not IRC. This is Social Stream Blade, and this is what, it's the same thing that's running in OBS to give us all of the chat messages on screen. This is essentially a slightly differently configured one that allows me to see what you guys are saying while I'm working. So when I'm in this view, instead of the three categories on the right there, because I can already see that on this monitor, instead I have this, so I can see what y'all are saying. All these tools that we use for streaming. I should probably upload this to GitHub so people can like look alongside, but we're going to be doing a lot of transformative stuff. Right click and cascade, but there is a tool for that, and it's on this Stream Deck. I would like a Steam Deck, but that would just make it easier for me to go to LAN parties. I have to lug my entire gaming computer back and forth, and all we're playing is Valheim. I might as well get a keyboard and mouse and a monitor and get a freaking Stream Deck. That'd be so much easier, but it's too expensive. I can't afford $700 right now. The last $700 that I spent went into a tool shelf. Before that, a mixer. And yet I haven't even done many gaming streams lately. I feel bad about that. We have not done gaming streams in like 6 months. And it's just because I've been too busy with stuff. It's been crazy around here. I've got a family member that's going into surgery on the 1st, and there's been a lot of crazy stuff going off in the background that I have not told you guys about. The long drive is calling my name. I know, it really is. Who played that the other day? Tomato played that the other day. He modded it to like within an inch of its life. I don't know if I want to do modded long drive. I would like to. I mean, Flatulent Gonad over the past like couple weeks got the 10K achievement in my summer car. It'd probably take me a lot longer than that, but I don't know if that would be a fun time for you guys because not a lot would be going on. I don't know. Yeah, if I wasn't on the public health program like assistance thing, I would be spending all of my money on diabetes and all of my family's money on diabetes. Not all of my family's money, but all of my money and a little bit of my family's money on diabetes, because this level of control I've never had in my life. My A1Cs have been a consistent level for the past couple months, and it's all down to editing my behavior now, which I'm very bad at, but I'm getting there. I'm getting healthier slowly. It's always, it better do it slowly than quickly, because otherwise it's not going to stick. That's my experience with things, especially with like weight loss and stuff like that. Like I need to build back into my schedule. First of all, I need to start waking up like at like a normal human being. I used to get up at 4 a.m. and go to the gym. Yeah, we got a, I don't know if you haven't been around, King. We got a dog like a year and a half ago. A year and 3/4 ago, actually. It's getting June's just around the corner, and then she'll be 2 years old. She has an ACL injury right now in her rear leg. Her passenger rear leg has an ACL injury, and so she's limping, and I'm not allowed to take her on any sort of a semblance of an athletic walk. But I was taking her on pretty decent walks, getting myself bit by bit more in shape and ready to do exercise. So I do morning, afternoon, and evening walks. Yeah. Boom, 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 boom. We're going to have to read up on Hagiwo's insane code now that we understand it a little bit more. We know that all of our hardware works, so now it's time to get into the signals and software. We'll do that in a minute. I'm just going to sit for just a minute longer and get acclimated to this whole streaming thing. I missed Tuesday because things were whack around here, so... I can't believe I got visually copyright struck from playing a Prodigy like music and having the YouTube up in the window on camera like this, and somehow it said, "Hey, you don't own that." And it's like, it's just there to be a placeholder to tell people that audio is and the stream is functioning. Utterly ridiculous. We need to get back to making a curio shelf that has active stuff on it that'll show that like stuff's happening during stream. When I have like a BRB screen up, the tourbillon was supposed to be the prize like achievement, a 3D printed clockwork mechanism that was like really fun to look at, and I probably could put like a little sign on it that would like rotate around and stuff. That would be really nice to have. We put it together and it didn't work, and I don't know, maybe I need to consult with Mr. Horologist or something. You may think that I have all these connections on Twitch because of the company that I keep, but I don't. I don't even know how I'd PM Uwo or Flatulent Gonad. I don't know who he is. He's an enigma. There's the Modular Synth. It's coming along, but mine was a combination of PLA and PETG. I think I did use a lot of PLA in it. And my printer was not as good as it is now. It wasn't as tuned. Tuesday, we will do Burn the Subs. That is my promise to you, chat. We will do Burn the Subs. I will drop the VCO stuff for a little while. And it's more likely whatever I learned today is going to be applied to working on the VCO on my own, because I need to do a lot of code manipulation, and I don't necessarily want to do that with you. But discovering how this program works is worth it. I got to get my seed starter started, and then put in a little thing into Node-RED that'll turn on and off a light when the sun goes up and down. Thought about making it, but it seemed like make work. There's a lot of work to it. Yeah, it's a very interesting project. It requires a lot of extra parts that you don't necessarily have. Like, everybody likes to use their own sized bearings instead of kind of like making a general universal size of bearing. No, they want to use whatever bearing sizes they feel like or they have on hand for their other projects, and so you're subject to that. And then you have to make the gear surfaces nice. So there's a lot of filing and sanding if I want to get mine working anyway. Those gears have to mesh nice and smooth for that thing to work properly. Let's get started. Get the music out of here before we get too into the next song. Hi, hello everybody. How you doing? Welcome to Friday at the shop, which typically should be used for cleaning up, but I am behind on things. I missed Tuesday, and so we're not as far along as I would like to be with all of my different projects. How's it going? We're not as far along as I'd like to be. This VCO continues to plague us, and part of it is that I need to know every single atom of the code and how it functions in order so that I can work with this stuff and so that I become more knowledgeable in how, at least for now, how digital amplification and damping and filtering and all that stuff functions inside of a modular synthesizer, like for instance the one that's sitting here. Burn the subs sitting there, I know, and I see that heatsink, that properly sized radiator sitting on top of the modular synthesizer, and I'm looking at it and I'm going, yeah, we got to work with that. And then I have the two dead analog VCOs. One sec. The two dead analog VCOs, one of them even has a filter in it, that also need my attention. And then there's also the seed, my peppers, my hot peppers I need to plant soon. So I have a lot of stuff on the table right now, including IRL stuff that's just crazy, and we'll get over it soon. But the boredom never seems to come. It never seems to catch up with me. Yeah, we got too much to do. But this VCO, I want to get a little bit of progress on it, and we did yesterday. We got all of the hardware vetted out. I now have made all of the corrections to the circuit boards, even though I got 20 of these things. I've made all the corrections to the circuit boards that I need to make so that they'll function. This one is still not vetted out yet. I would like to put parts even on this board and do the modifications that I need to do in order to make it work and test to see that it's working. And we can practically use the same test program. I just need to switch one of the switches over to a knob. Easy to do. That's something that would be maybe on the horizon for us. I don't have the parts for it right now. So we'll put that on the back burner and we'll get to that. I won't order boards yet. I'm not allowed to order boards until I get both of the circuit boards hardware fully functioning. Yesterday we made a lot of progress. We made sure that this board right here, come back over here. Ah! This one right here functions. So we have all of the hardware functioning. The only things that could potentially need tweaking would be the filter on the audio output and cleaning that up a little bit. I don't think it really necessarily needs it, but that's something that could maybe happen, and that's just part values, right? That's not traces that need to be rerouted. So as far as we're concerned, all of the hardware on this thing is done. Now we got to look at the software, because I don't understand how the software works. The explanation was in Japanese. We used Google Translate on it. It's not really so much a translate thing because it works how it works, and explaining how it works can only happen in so many different ways. Maybe the sentence structure of the Japanese language might not lend itself to understanding precisely how this works, but I don't think that's the case. I don't think that's the case. And there's not a lot of colloquials in turning a PWM signal. It's just like math, right? And so we should be able to understand that without language, practically. So I have looked up a couple things. I have a few resources that I put in my streaming projects section that we need to look through, and we need to figure out exactly how this program's working. And then we need to take an aside and we need to read up exactly what this program is doing, how it's functioning from end to end, and figure out how we can work in our own code that we understand into it. That's something that's more for me than it is for you, but maybe you guys can see a little bit of my process here. We're basically reverse engineering software that we don't really understand how it's working. What's up, Baloo? So first things first, I need to go to my stream project section, and I discovered that in 2017, Elliot had already beaten me to the punch over this stuff. This is an entire thing. Don't Fear the Filter, low pass edition. So this is a whole thing on Hackaday. And I do like Hackaday because I like the way these guys write. You know, I worked for them for a little bit, so there's a little bit of bias there. I don't know, I just think they're neat. They do good stuff. And so every now and then I'll run into something on Hackaday that'll completely change the trajectory of all of my projects. But anyway, this is an Elliot Williams article from 2017, and it explains a lot of good stuff about filtering. So what we're trying to do, today we're considering low-pass filter, specifically the Sallen-Key filter with Butterworth characteristics. The Sallen-Key filter in all of its different various forms is a workhorse. And what we're doing here is a fairly common thing. We are taking high-frequency PWM, as in inaudible PWM, and we are translating that into an audio wave. Now, although this one is centered around 0, this one starts from 0 to number. You put it through a capacitor and it'll do that. But if you put a bandpass filter on it, what it's going to do is smooth out all of those waves, and the PWM, the pulse width of that wave, is going to determine how much energy is in your signal. So right here, you see this big gap, right? There's a big gap, and that means that there's a lot of energy. This is being held at whatever it is, 3.3 volts, at a longer amount of time, and that's what creates this high voltage. I guess you could call it high voltage. The lower voltage, you've got much smaller gaps on. So there's this, well, it's a larger but low gap. So you can see it like there's a grouping of high for when the signal goes positive, and there is a grouping of lows when the signal approaches 0. That's sort of the whole point of it, is the amount of energy in that PWM signal takes the form of that AC wave. And we turn it into an AC wave just with a capacitor. You put a capacitor in the way, and the properties of the capacitor will shift it from positive to negative instead of it being from 0 to 3 volts. So if you were to look at this on the same number scale and you were simply putting resistors and capacitors in the way, this would technically be 0 volts and this would be 3 volts, but instead it's 1.75 or something, and negative 1.75. So that's essentially what we're trying to do here. And I guess the way that we're doing it is we are modulating our waveform signal with the PWM. How is that done? I'm not sure. So you can see here, it's ratio of positive to negative determines essentially what the overall voltage of the wave is. And so when the ratio is mostly positive, we are mostly at our top voltage, and then it starts to taper off as we go more towards the lower voltage. And all the roughness is from the op-amp switching as well as the filtration properties of it. And there are filter design tools that'll help you do this kind of stuff. So this is a lot to read. And the Sallen-Key is essentially like a common thing to do this with. That's all well and good. That's all the hardware stuff, right? That's how we get outputs from different varying filters, and how we can use Sallen-Keys in the inputs. We don't need to do that. Good article. I read it earlier. I skimmed it earlier. I didn't get all the information about it. I also put a couple other links into my Discord. One of them is this website, sim.okawa-denshi.jp. What this has is a bunch of different filter tools for calculating these things. It's in my stream project section in the Discord. But these are a bunch of different tools. So if you know the parameters of your filter, or if you're trying to figure out what the parameters of a filter is that you're studying, you can punch them into a calculator here with your R's and your C's, and you can get all the data on them. There are also sample calculations too. But these are good little tools that keep you from having to do math. And then finally, oh, this is a different one. This is somebody else's guitar pedal that I wanted to just put in here because this is kind of a cool circuit. They are doing some Sallen-Key filtering, but they're also feeding stuff back into a weird circuit like this, and it's only using an MPC 6004. So I have no idea what this does, but it looks like it does cool stuff. Looks like you could probably give it a PWM and get some really weird stuff out the other end. All right, anyway. That was just part of my research on the Sallen-Key filter. What we need to do is figure out how this software is functioning right now. And it seems there's a couple different things going on here. There's an octave select, there is a mode select, and then there's a mode switch, which I think is for the type of modulation. One of them is wave folding, the other one is frequency modulation, and the last one is amplitude modulation. Obviously, amplitude modulation, you change the amplitude and that gives you a signal on the output. Frequency modulation, you change the frequency up and down and that changes the amplitude of your output, audio wave. Folding, I don't know what's going on with that. I don't think that's phase modulation, but with a PWM signal, I guess you can either control how much energy, you know, how many volts go into the PWM signal, or you can control what the pulse width is, and that'll give you sort of a frequency style modulation. That's my thought on that. I need to close the window. I'm freezing cold. It's actually a deceptively cold out because it's like, it's super sunny and like nice and all the grass is green and stuff, but it's freezing cold. We got that Canadian air sneaking in and freezing us to death. Much like their geese, their air is also very aggressive. Let's close that. Maybe I won't freeze to death. All right, so. Oh, I have a whole bottle of seltzer over here. So, what are we gonna do? Well, first we need to figure out what this thing is doing in one particular mode. So I think the mode that we were working with was, actually I think the mode we were working with was wave folding. I don't really know what the hell's gonna go into wave folding, but we can take a look at it first. It's gonna be really confusing, but we can write down all the equations and see if we can simplify things a little bit, because there's two different like tables that this thing generates on the fly. And I want to turn that into basically, like the title said, these equations are made up, these equations are polynomials, and I would like to take the nomials out of the polynomials so that we can affect the nomials and then poly them. We can put them all back together as one big thing. So what is going on in this software? Well, let's start from the beginning. Don't let that table scare you. I don't think we're really using that table. Include hardware pwm.h. pwm.h is it's a Raspberry Pi library, I guess, that helps you run your PWM stuff a little bit more closely. Because what we're doing in this program, and according to who's this guy? Buchow. According to Buchow, the way that we're doing it is we have a PWM engine inside of this Arduino. And when the PWM engine is determining how it splits up these waves, it's doing it in steps. And you can put a lot of steps into your PWM. For us, the magic number is 256. So we have 256 steps, and whatever clock tick is running inside of the microcontroller is going to step 256 times, and it's going to use that resolution to figure out what the PWM output should be, whether it should be high or low for that 256. And what that'll allow this thing to do is to, where did that go? I should pull up the Hackaday article again. Those visuals on the Hackaday article are like perfect. What in the 256 steps, it'll go, well, how long do I need to be high and low for? So it's like in 256, it's 0 to 256, and it'll go low, low, high, 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 or it'll go high, high, or it'll go low, 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 high, high, right? So it'll determine how long it's low and high in 256 steps. What our job is to do is to go through those steps and tell it what to do. Tell it whether or not to be low and high, and or translate it back into a number from 0 to 256, I suppose. Or no, it's 0 to whatever the resolution is, I'm not sure. It's done in 256 steps, so it boils down to this, but I don't know if there's like 1024 ticks or what. But so what I guess we're doing is we're taking a wave and then we are turning it into a step function of energy in order to frequency modulate it. And amplitude modulation, and this is just a guess because we haven't looked at it directly, but in amplitude, where is my window? In amplitude modulation, I suppose what we're doing is we are altering the height, altering the voltage level of the output. And so the PWM tools, the Raspberry Pi PWM tools, allow us to affect the amplitude. So we can have frequency modulation, we can have amplitude modulation. Wave folding, I have absolutely no idea. I don't even know if it's covered in here. And then we have different waveforms as well. So there should be equations for that, square wave, saw wave, etc. this is a lot. This is a lot. And right now, I believe I'm looking at wave folding, and the wave folding involves a lot of sine equations. This one is Vogt Pow, and it's not really even needed. It's not really even needed. This massive table, that's what these numbers are. This is supposedly 1230 entries, 6 octaves. And we have a bunch of settings up here. Let's just go down to our code where it starts. So we start with setup. Setup is run once. And in setup, we set up all of our pin modes. For some reason, there was a setup 1 originally in the program. This isn't necessarily the original program. I think I edited it a little bit. Actually, I think all I did was paste this in. So these are just setup 1 is not something that the RP2040 under Raspberry Pi does. Hagiwo, I believe, originally coded this in a different language and then translated it over to Arduino. So we might be missing some things. We might want to look at how the other program works and read through it. Although this probably works, it just does a couple things that are not good. And if this wasn't a linear table of values, then this might be a valid thing to do. Oh yeah, it looks like I got my fingers into this a little bit. So like where I set the wave table is where I do this. But what this does is this basically sets frequency table of I. So it takes frequency 0 times 2. Well, power, does that work oppositely? Let's open up Arduino. We're going to be in Arduino CC a lot today, and you guys are going to have to deal with me being a little bit scatterbrained about everything. No. Whatever. Reference. Pow. Ba-boom. Value another raised to a power can be used to raise the number of fractional power. This is used for generating. Yeah. Base. Okay, so base 2 and then the exponent. So it's 2 to the something or other. So this would be 2 to the Vogt power table. F0, and that's our frequency table of I, and that's for entry 0 to 1230. What is that even doing? So in order to make any sense of this, I'm going to start up a little list of things here down here. So let's get our pencil going. I could draw a line. No, pencil is the way. We only use the pencil here. So what I don't understand is 0 to 1230. This is F table is equal to F0 2 to the Vogt power table. I might have to get a piece of paper and actually do this. But then Vogt pow is equal to, and then we have an equation for that. And this is something that one of you guys came up with for our actual code. Where is that? All the way down here in table set. These big tables are not too bad for this microcontroller. Big tables like this used to be kind of annoying with microcontrollers, but nowadays they've got so much storage, it's just not even a thing. So this one's a different table. Oh, here it is. Octave select. Number of octaves, so it would be 2 to the, well, we don't have to worry about the power, but F0, 0 to octave resolution, and then we have number of octaves times I, so 6 times I over that's 10, wait, what was the resolution? 1230? 6 over 1230, huh? Yeah, 6 over 12, 6 over I over 1230. 6 times, rather. Probably better represented as 6i. So we are spreading those 6 octaves over 1,230 entries. To what end? I mean, what are we getting out of that? I goes from 0 to 256. Or no, from 0 to 1230. And then from 2048 to 1230, I plus 1230 is equal to 6. Why would it do that? Or so from 1230 to 2048, I plus 1230. So it's just 1230 to 2048, F table is equal to 6. So this would be from 0 to 1230 times 6. Because I would equal to 1230, and it's 12, or no, it's 0 to 6. No, that doesn't make any sense. Wait a minute. It's 0 to 1230. No, it's not. I'm dumb. I'm dumb. Where's the calculator? Where's the calculator? I'm too dumb for this. It would be 6 times 1230 over 1230. Which equals 1? No, it equals 6. Yeah, so it's equal to 6. Why would it go from 0 to 6? I guess it's 1 volt, because it's 1 volt per octave. 6 octave. So it goes from 0 to 6, even though that's not... We can't really get to 6 volts. We got to... Did we get to 5 point something? I think we might have. I was giving it the full 6 volts, but it wasn't reading it back. But that's frequency, not voltage. So I guess it's just a convenient number. It's a convenient number that represents the amount of volts that we get in anyway, even though we technically our range is from 0 to 5 volts. So working through that, I mean, that's just the frequency table. So we can just generate that with the equation. Two to that power, huh? How does that work? That gets into my controls experience. All right, so we've got this big table, and the big table is represented by 0 to 6, just about. And it's got a lot of entries. We start at 0, we go to 0.00, we charge our way all the way up to 6.0. But if it's 2 to the thing, wouldn't it be 2 to the 6? That doesn't make sense. Why is it 6? How do you do that on this calculator? I don't know how to do that. All right, cancel that. Clear that. Strange. All right, anyway. So we're taking that number, and I'm probably missing something. Anybody can clue in and give me a little bit of info on this stuff. Make sure that I have all the windows open so I can actually see you guys commenting. Nobody said anything. Cool. All right, GPIO function 2, GPIO function PWM. So that's where setting the PWM function, and then we are setting slice number, because apparently we are setting slices to certain things in order to affect control over this. So resolution is 1023. Again, this is all the table value inserts. I don't know why our table is doubled up with the number 6 though. 1230 to 2048, we're just setting to the number 6. That seems odd to me. Maybe it's just in there for scaling at a later date. PWM set, slice number true. So slice number 1, sys clock, resolution plus 1 over frequency. Slice number 1. May have something to do with 133 megahertz, which is what we're running at. So running at 133 megahertz, there's going to be a little bit of tuning involved in order to get the frequencies to line up, because the PWM engine is running at the system clock frequency. So we have resolution plus 1, sys clock. What do we have? Resolution plus 1 times the frequency, and then we divide system clock by that. So that would be sys clock over resolution plus 1 times frequency. So it's 133 over 1024, or sorry, 1031, 1231. 133, that's kilohertz, that's megahertz, over 1231 times the frequency, which is a big weird equation. Big weird equation. Why that is equal to 1 is beyond my recognition. If the frequency is that high, which I don't think it is. So on PWM wrap is the next function. So let's just assume we've set up all of our PWM functions here. We're ready to do the business of very fine slicing of PWMs in order to affect the frequency. So the base frequency being what we represent as the PWM's highs and lows, I suppose. So on PWM wrap, so that's when the PWM step number gets all the way up to the top. So when we have done the business of making whatever wave it is we've made, and I could show an example, the good looking one from, there it is. Okay, so this one right here. So what we've done is we have counted all the way up, and then we wrap around to the next signal. So the previous signal's done, we've wrapped around, and we're ready to start from 0 to 256 again. So for this 0 to 256, we need to affect essentially a voltage level that corresponds to the voltage level at that point of our frequency. So what we have is we have clearing the IRQ. F is equal to F plus oscillation underscore frequency. Osc frequency right now we are taking control of. We've set the number ourselves. I guess, why is that way? If F is greater than 255, F is equal to 0. So I guess we're rewriting that Osc frequency constantly, unless, why would F plus oscillation frequency? Int K is equal to the integer version of F, which is an integer of the frequency. PWM set channel level per the slice number. So the slice number would be, as we step through our PWM, channel A mod 2 wavetable of that position plus 511. What the okay. So we move up 511 from where the mod wavetable of K is. Int K is the integer of F. So wavetable position of K of the mod 2 of the wavetable is that position in the F. Where is F incremented at all? F plus the current oscillation frequency. So what if that changes mid-loop? Because that doesn't exactly acknowledge, we have to get through the entire 256 round of that frequency. K is equal to int F, slice number, PWM channel output, mod 2 wavetable of K plus 511. So we're adding 511 to whatever the wavetable says for some reason. Seems a little weird that we're doing it here. So this is a little bit premature. We probably should look at this when we've got a little bit more of the information going on in here, because I don't think F is fixed. Float F is equal to 0, and we'll probably reset F as we go along. And we still need to make that mod wavetable. Okay, so we're a little premature for this one. Let's come back to it. In our main loop, old push switch is equal to new push switch. So if this is a very rudimentary way. They're not using a bounce engine on here like I do. I like using bounce because bounce requires you to hold the button down for a little bit and for something to happen. That way, in microcontroller time, which is very, very short increments of time, when you push down on a button, you're fighting back against the spring. And so as you fight back against that spring, your contact point is triggered multiple different times. You press down on that button, sometimes you press it hard enough and all that energy goes down and then back up, and you get a little bounce back on that. What's called bounce. That's the reason that it's called bounce. It's a very simple concept. But bounce is important to consider because microcontrollers are extremely fast, and especially if you're just starting out with this stuff, you will make very simple programs. And those very simple programs, the microcontroller will go through not in the blink of an eye. It'll go through before the signal goes from your brain to your eye muscle. That's how fast it is. So if you have a bouncer on there, it can say, hey, this has got to be low for a certain amount of time before I actually acknowledge it. And there are ways to do that in code, but it's much easier to just use a library. This is one way of doing it as well. If your loops take long enough, when you come through with your loop, you can check to see if the state of the switch has changed. It's much cleaner to look for like a rising edge or a falling edge, but if you do a switch change, you can get away with this, and sometimes your buttons might go a little crazy and double hit. There's enough calculation load that this thing has to do after the buttons hit that I think it probably delays it enough that that they can get away with doing this. Do that. I can actually see what we're working on. So anyway, this is a way to log whether or not the button has been pressed or unpressed. If digital read 0 and blah, blah, blah. So we have an octave select that's going on here that's basically just selecting a number based on the state of the switch. So if we have the switch up like this, because the digital pins that these switches interface with are 1s and 0s, right? And so you have 2 positions and 3 different switch modes, squads. So one of the switch modes, you're shorting out one of the switches, and in this case, I think it's P4 that you're shorting out, because the way these toggle switches go is when you have the switch in the upper position, you can think of that as a line going down this way, and so the common and the lower pin are shorted. When it's in the middle, neither of them are. Sometimes you can't get to the middle depending on the configuration of the switch. When it's down, you can think of the line going through it going to the upper 2 contacts. That's how it works. So we kind of coordinated this, and I don't know if I did it properly or not. I don't know if I have these labeled quite right, but it's functional enough for us. When we have the switch in the up position, apparently the P0, these are probably the opposite of what they should be, to be honest. I think I messed that up. But anyway, when it's up like this, these 2 are shorted out, and so we get digital read of 0 is equal to 1. Sorry, we get the second, actually the second instance here. We get 0, 1 like that, and so our octave is 3. So that's selecting the 3rd octave. In the center position, they're both at 1, so we get 1 octave, or octave 1 above. And if we are at the lower position, then the lower one is a 0, or sorry, the upper one is a 0, and the lower one is a 1, and we get a 0 octave change. This goes the opposite way. Maybe it does. It's 0, or sorry, 0, 1, 3. That's probably how it works. I'll have to correct that in the code. I just kind of got it wrong last time. I forgot to consider how switches work. Mode select. So FM, AM, and wave folder. When we're in wave folder mode, the switch is up. I remember that from the board markings. So when the switch is up, that means that digital read of 3, P3 down here is 0, because that one is shorted to ground and the pins are input pull-up. When we are in FM mode, oops, that's the wrong switch. When we're in FM mode, the switch is in the center position, and so we get 1, 1, so that's 1 for FM, and then down is AM, amplitude modulation, which is 4, P4 at the top is at 0, and then P3 is at 1. So very simple method of doing this. That sets what mode we're in. We're going to start, I guess, we should probably start with frequency modulation, right? We were looking at wave folder. That's the one that I think that we implemented in our original code, and that's, I think, the more complicated one. Let's look at one that's a little bit easier. So we're going to do octave is going to be at 0. We're going to assume a 0 octave for our math, and then our mode is going to be number 1, FM. So just remember that as we go down through the code. Now we're doing a frequency calculation. For what? Analog read of pin 26 times calib. So calib is just going to be a compensation for resistance errors. ADC is equal to analog read of 26. Clibber, what are you doing, Clibber? How you doing? Resubscribe to the tier 1 for 20 months. Long time since I subbed, been watching you a lot before starting work at Volvo. Hey, that's really cool, working at Volvo. So you got 3 weeks working for them. That's pretty cool, man. Good to see you, Clibber. Yeah, I haven't seen you in a little while. It's people come and go, and I try to remember names. We're doing kind of a hardcore code read, so there's a lot of stuff going on in here. A lot of stuff going on in here. So I guess what we're doing first is we are reading from our 1V per octave. Is that right? Yeah, P26. So 26 is 1V per octave. Control voltage. So that would be ADC. Oh wait, read. CV. So ADC is equal to, and this is analog read of pin 26. So that's 0 to, I believe it's 1024. Yeah, 0 to 1024. That's analog in. And that goes to, multiplies by a calib. And then what we do is constrain it to 1225. So constrain zero to, and they're saying 1225. Six to 1220. Oh, 6 octaves equals 1220. One, two, two, zero. And it gets unstable outside of that because of the way the transistors work and stuff like that. With the filters that we're using, they're pretty basic, and so if you get outside of a certain frequency range, things get a little squirrely. The system becomes a little bit more unstable, and you can run into trouble. So I guess that's why we're doing that. We are just stable for 6 octaves, and that's 0 to 1220. So we limit it to 1225 and get a little bit of overrun on that. And then the frequency pot. So map the pot. And that's from 0 to 1023, 0 to 127. Back to 0 to 127. Half of 255? No. 127, I mean, that's like a common number, but why 127 is strange. That's very little effect on what's going on. I guess that's a fine tune. What the heck? Madamu subbed for tier 1. Hey, Madamu, thank you very much. Hey, I appreciate you subbing. That means a lot to me. Cool, we haven't seen a lot of subs lately. introvert submode. Sorry, but you get thanked. I don't want anybody getting mad at me for not announcing. ADC plus the frequency pot. It's a freak table. The frequency table of... Oh my god, my dog's going nuts. I think her friends are out there. Pot plus... What are we adding to that? We're adding the potentiometer plus the ADC value. So the entry is equal to that scale. So it's from 0 to 1220. So the potentiometer is mapped to 127. So pot is 0 to 127. And the ADC is 0 to 1225. So the max entry is going to be 127 plus 225. 1, 3, well, 5, 7, 8, 9, 10, 11, 12. There's 2, 5, 3. 1352. So 1352 is well out of the range, but the frequency table of 1352, that would be equal to 6. Because we've written over entries 1230 to 2048 with the number 6. So that's essentially what it tops out. It tops out is essentially what they're trying to do. Okay, we're starting to get this a little bit more. So our oscillation frequency, what the fuck is this? So then we take this, and it's 256 times what is divided by that? Is it all of it is divided by that? I hate it when they do this. They just multiply it out in front of the thing, and then they don't give us any more information. It seems like frequency table is divided by 122070. Now, is that the clock frequency? In which case, ours would have to change. And they multiply that by 1 over 1 plus octave. Max is 3. So 1 over 1 plus 3, 1 over 4, which is a quarter. Put a lot of question marks everywhere. 256 multiplied by frequency table over 12270. 122070. That's the clock speed. That's the frequency from the frequency table. 256 being, I think, the number of entries that we go through until we wrap around on our PWM wrap. So if F is greater than 255, now this isn't F, this is, what are we calculating here? We are calculating, oh boy, where are we? OSC freak. So that's our oscillator frequency. So what did that accomplish? What we've done now is we've read our control voltages in, and we've read our potentiometers in, and we've multiplied and constrained them into their appropriate values. And then we added them together in order to give us a frequency table entry. That frequency table entry divided by the clock frequency applied to whatever our octave selection is, which could be 1 over 1 plus 1, it could be 1 over 1. So it's basically a quarter. No, hold on, wait. Get rid of the question mark. 1/4, 1/2, or 1. Or 1. So we either take it at face value or we take a fraction of it, multiply it by 256. That is our osc_freq. Hopefully I can make that a little bit more clear in the future. and actually the frequency selection applies differently for the different modes. I don't know why we're doing this just out in the open. So depending on what mode we have selected, we haven't even gotten into that yet. We've just made that variable. All right. The mod parameter set, this is where we're looking at. So mod is dependent on mode. Mod depends on mode. And so if mode is equal to 0, let's do mode 0. Mode 7, mode 0. Constrain. Oh boy, what the 0 to 1023. So it's 29 and 28. So it's the CV and the pot. 29 and 28. So CV plus pot. Zero to 1024. 0 to 1024. And we're constraining it from 0 to 1023 and dividing it by, oh wait, no, that's the wrong one. 0 to 1024 plus 0 to 1024. So essentially we're taking the sum of those two and then, that doesn't seem like a good way to do it. I would rather take like the whole, well, I guess you want your control voltage to have as much effect over it as possible, but it's like your knob and whatever your control voltage coming in is, they're gonna like mix together, but they can easily throw each other off. Like if you turn it all the way up and you give it a full control voltage, turn it all the way down, you give it a full control voltage, and that full control voltage gets the whole range. So I guess you'd want to turn it all the way down if you're not using the knob, and the knob can affect whatever you're in. Of course, we're also scaling it after the fact, so so take that, constrain. Zero to 1024. And then you multiply it by 0.0036, and then you add 0.9? What am I gonna do? Like number 0 to 1024 times 0. My notation's going to be all over the place, by the way. You guys will just have to tolerate. 0, 0. What is that fraction? 0036 plus 0.9. That's 0.36%, or no, 3.6%. What is 3.6% and where is that coming from? I'm going to Google 0.0036 and see if anything comes up. Ah, BTC to USD. Bitcoin to US dollar. As a fraction. 9 out of 250. That's not quite 6 over. 6 over. Not quite. 9 over 250. Three fraction digits multiplied by 1,000. Blah, blah, blah. Last step, simplify. 36 over 1,000. That's got to come out to something. There's got to be some kind of a justification for that 0.0036. We're dealing with two 0 to 1024 values, and we're mapping it onto something that, you know, to excuse all my handwriting here. System clock over 1231 times frequency. Could that equal, what about, what is it? It's 122 megahertz. Where do we get that? What was that number again? 122070. 122070 divided by 1231. Nope, that's 99 point, well, actually 99.163. 003. That doesn't make any sense. No, that doesn't make any sense. I don't know what this built-in calculation is going on here. 3.6%. And then we have 0.9 following it up. So we're putting like 10% of 1, scaling that down maybe. Is that 1 over? Well, 1 over 1024 is 0.0009. Yeah, there's some kind of frequency calculation going on here. Well, the amplitude is, wait, the amplitude is much less than 0 to 3 volts, right? Maybe it isn't. I don't know. I can't figure this stuff out. And then let's do mode 1. This would have been better on a notebook. I've neater handwriting than this. I'm writing with the mouse right now. So let's skip over to mode 1 and see if we can figure anything out about that. So mode 0 is AM. And then mod is equal to. So mode 1 mod is equal to, and again, it's this same thing. It's CV pot constrained 0 to 1024. (1023), whatever. I'm going to call that 1024, but then we're dividing that by 8. Why are we dividing it by 8? Well, 1024 over 8. 128. So that equals 0 to 128. But we have 256 rounds, and we're not exactly reaching 50-50 here. We have 0 to 1024 constrained to 0 to 10. We have two 0 1024s added up. We constrain them to 0 to 1024, and then we divide it by 8, which gives us 0 to 128. So we can only get to halfway through, or is that gonna No, the CVs and the pots don't go negative, but maybe that's 128 is the amount of control that we have over the rest of everything. If we're amplitude modulating, we have 0.0036 plus 0.9. So, you know, PEMDAS, right? Parentheses, exponents, multiply, division, addition, subtraction, and division and multiplication can flip around. But, well, that depends on how the microcontroller evaluates it. That's why we use a lot of parentheses when we do things in microcontroller math. But this thing should essentially evaluate first, because this is the first two steps. And the first two steps is adding the CV and the pot, which can each run from 0 to 1024. And then you can strain that whole business to 0 to 1024. So basically, you have control over like very little, and it's easy for the thing to kind of max out. Unless you turn it all the way down, I guess. Turn the pot all the way down, it'd be nice. If this is unplugged, if the CV is unplugged, then that's 512. So when it's unplugged, that's 512. So you don't get, because it's addition. It should be addition or subtraction of the CV, shouldn't it? Maybe that throws it off because you're using one to tune the other, I guess. So if you turn it all the way down and then you give it a CV, you can then tune an addition to it. But you can't tune a subtraction to it. Wouldn't you map that from negative 512 to positive 512? Or at least from a negative number to a positive number. So that's just one of my questions. What's up, Groovy? We're kind of going through code pretty deeply right now. It's not I would love to be working on RC car stuff today. I know I'm going to get parts for the car today, but I would love to be working on that. I try to keep Fridays light. We have no choice. We did all the hardware yesterday, and we got all the individual hardware things working. Like, look. Oh, wait, I don't have the power supply on. I'm going to turn the power supply on this thing. Let's go ahead and turn it on. Hold on, I got to unplug output in order to juice it up. It doesn't remember your settings from the previous session. Plus or minus 12 volts. We'll just give it that for now. Now, keep in mind, the code is not working on this. So I'm not running that code. We are running just our sample code, which only gives us one singular waveform with some preset numbers that we put in. Doing the first mocks. Oh, ripping every weed out before they wake up for spring. I need to plant my my hot peppers. I've got this hot pepper kit sitting right there, and it comes with a couple grow lights. And then I spent the time the other day during my executive function meltdown to program up a bunch of these sawn-off switches. And what I can do with these switches is I can go into node red and I can do a day and night cycle node and run that into the node that controls this thing. And so this thing will just automatically turn on and off with day and night. And then I can just keep water in the thing, and eventually I'll have seedlings that I'll plant once spring hits. But if I keep it here, it'll be around 70 degrees, assuming the Canada air doesn't get in through the window too much. Don't you guys have Canada air down there? We've got it up here. It's freezing today. Because of all the instability that global warming is fucking doing. Let's make ourselves a lot more room. And I'll do a line down here. Okay, so we're working through how this program works, and I'm taking notes as we go because my memory cannot keep up with this stuff. We're looking at how this program does the business of what it does. That way, in the rewrite of the program, I can make everything kind of my style of organization, and we can pull polynomials out of, we can pull the nomials out of the big polynomial. That's what I'm hoping to get to today. Chilly but not terrible, 53 and cloudy. What is it like in here? It is It's actually 72 degrees in here, but I feel freezing. I feel like it's very cold. I'm gonna pull up, what is it? Merry Sky, and figure out what's going on around here. Let's see. We are Flood Watch. What? There's supposed to be rain this afternoon? What the fuck? Oh, wait. That's not near me. Why did it say, oh, Mount Holly, New Jersey? Why is it warning me about that? Wait, why is it warning me about that? That's not even me. Where does it think I am? Clear. Light rain. Next 24 hours. Oh, I see. Saturday is within the next 24 hours. I see what it is. It's 41 degrees, so I guess it's not that cold. Crazy rain tonight. Jeez. This fucked up weather, man. So amplitude modulation mode takes the sum of the CV in the pot, limits it, which I don't like this. This needs sort of a redo. This needs a redo because we're limiting everything from 0 to 1024, and then we're constraining it because we're adding two numbers that could be 1024. We're limiting it to 1024, and then we're applying it to whatever equation scales it for the different modulation types. And what that's going to do is that's going to make both of them adding up linearly is not. Having one add or subtract from the other would probably be a good idea, because if you don't plug in a control voltage, you've got 0 to 1024 control, but one of them is stuck at 512 at all times. So I'm adding 0 to 1024 to 512. That needs an edit. That needs a big edit. We need to limit one of them with negative numbers, and then constrain it from 0 to 1024. Hot pepper aside, some of the best sauce I've had is Viet sauce called State. Not satay. Oh, it's satay, not state. Not sate. Juice up some pho. I've always done sriracha on pho, and then I go way too deep into the hoisin sauce. I can't eat a mouthful of rice noodles without putting a shit ton of hoisin on it, and it's kind of a bad habit. That's really, you're supposed to pat the meat with it, right? But I'm just like, I put it on like toothpaste and just eat the whole thing. It's a bad habit. Mode 2. Mode 2. And this is wavefold. I don't know why it was, I don't know what happened in there. So mode 2, mod, is equal to so we're going from, we're going in the opposite direction, 1023 minus, which is an odd choice. So it'd be the addition of those and then constrain them. So 1023 minus this whole business here. It's like I lose some pixels on it every time I cut and paste it. So once again, it has the same type of limitation that I don't like, which makes adjusting it a little bit weirder. Where's that line up? Same thing. It's not quite right. It's okay to do constrain 1023 minus constrain. I mean, you could also like turn around your constrain elements, and I think it might have the same effect. Or you could multiply it by, no, that doesn't quite work. But like the Madame U, the one of the better sauces that I've ever had was actually sent to me by the other Lone Star. I was going to send him some hot sauce, and I never did it. I really should have, but not hot sauce. I had a hot relish that I had out of the garden peppers, but he sent me this bird's eye Thai sauce. I don't know what it was, but it was very good. He fermented it and everything. Probably bird's eye peppers, right? Yeah, it was really good. I put it on a whole bunch of different stuff. For some reason, wavefold mode has to go from 1023 to 0. This gets constrained and then applied to that. It's a very simple thing, but it's kind of a strange equation. And it seems like, you know, considering the way that we're looking at this, it would be better to handle the analogs and then do this mode stuff somewhere else. So you would get this number as a function, like you'd come in here and you would add up your two analog reads, and then you would constrain it properly, and then you would do something depending on the mode. So you'd boil out all of your elements until you've got commonalities removed. And the commonalities that I see is that every single one of them does this. And so you'd pull that out of here. Of course, this one also, they all constrain it as well. So it'd be that element, but you'd also fix that so that it would be influenceable in both directions. Then we read the push switch. The push switch. We're reading the push switch. That just changes the waveform type. Again, so switch equals waveform. I can't do W's. Wave type 0 to 7. Then parentheses, it's mode dependent. Dependent is a very tough to write word. Mode dependent. So now we're set up with all of our outside stuff, right? Now we go on to modulation. On to modulation, rocket ship. Yeah, rocket ship. Off we go. Okay, so we take the rocket ship up to modulation, and now we're at modulation. What in the holy hell happens to modulation? This is where things get stupid. And I'm using the thin marker intentionally. Usually I thicken it up like that. But we're using thin marker because I'm probably going to have a lot of notes on this. This was going to be loop 1. Apparently, I guess in a threaded microcontroller, I suppose they probably have loop 0 and loop, or you know, the main loop and then loop 1 and then loop 2 for your different processors that are doing stuff. But in this case, we only have one, so it's commented out right here. We comment out loop 1, and we put modulation just into our main loop. And this is, again, I don't like this style of coding because our main loop should not be the bulk of our code. The main loop should not contain all of our code, and it shouldn't contain any numbers. There should be at maximum, one number in the whole thing. There should be no numbers inside of your loop. Your loop should be a list of tasks that boil down to the functions. And even then, the functions should be another list of tasks. Just because when you get to the more complicated stuff and when you get back to your code after 4 years, you look at it and you go, what in the hell, what's happening here? And you just don't know because you don't know what the source of all your notes was. It's much better to have a list of functions as the main loop. So anyway, loop 1 is supposed to have been used sort of like a function in that now we are doing the business of modulation. And I suppose in the background of this program, the business of modulation would have been going on at all times anyway. So we are creating the mod wavetable. I still haven't seen any service paid to output. I don't know what this thing is doing during this period of time. So if mode is equal to 0, so wavefold, mode 0, wavefold. And then mod wavetable, 0 to 256. So we're doing 2 rounds. 0 to 256 mod wavetable is equal to wavetable of I times mod. Okay. That's it. Which calls into question the logic of adding the two ADCs together and making it so it's 0 to 1024. Well, this number is 0 to 1024. What does that do for us? Does it wrap? I don't think it wraps around, because if it's wavetable value of I, that's right, wavetable value of I. Okay, so that changes things. That's not the entry. So for the wavetable entries of 0 to 256, we're taking 256, but we're multiplying it by 0 to 1024. How does that make sense? Is that wavetable of I for like 1? For 0 we get 0. For 1 we could potentially get 1024. For 2 we would get 256, or no, 2048. Zero we get 0. 1 we get 1024. 2 we get 2048. Entry 2048, entry 1024, or entry 0, entry 1024, entry 2048, etc. It's not like we're taking like a modulus or anything like that. Wavetable of I times mod. But then we're also in wavefold mode. And wavefold mode is 1023 minus that number. What? Mode is equal to 0, wavefold. 0 to 256, wavetable is equal to wavetable times mod. And then we get the fold. So then fold. Fold? What the fuck? I don't understand this at all. So 0 to 256, 512. So for 0 to 256. And how many entries are in which one is it? Mod wavetable, mod 2 wavetable. Mod wavetable and mod 2 wavetable. Mod wavetable, mod 2 wavetable. They only have 256 entries. So we start with the mod wavetable, and then we move on to the mod 2 wavetable. And so we've made our first, well, we've made the mod number, and that's based on where our knobs are set and some weird ass equation. And then we are, well, that's for, oh, that is for folding. Wait a minute, I looked at the wrong one. This one's fold. Fold, and then AM, FM. Fold, FM, AM. FM is over 8, so fold, FM, AM. Oh man, what am I programming? This is a voltage-controlled oscillator, and what this does is very commonly used. It basically runs through the PWM and it figures out what the, well, okay, depending on the modulation, it's modulating PWM and putting it through what's called a Sallen key bandpass filter in order to create the voltages of the wave. So as you run through, this is for instance a pulse width modulated waveform. You get these weird wibbly things, but what you can basically see happening is when you have the PWM frequency biased towards low, the voltage output will bias towards low. When you have the overall PWM frequency biasing towards high, you will get high. And so it adds up and it subtracts from itself, but it basically allows you to take this PWM signal that a microcontroller can put out very easily and turn it into an audio wave. And so what we're doing is we're looking at how this other code works. This code is from a fellow named Hagiwo, who's a YouTuber who creates these amazing, cheap modular synthesizer circuits. So you can go to note.com/solder_state and you can take a look at some of his projects, or you can look up Hagiwo, there it is right there, Hagiwo on YouTube and check out some of these things. But I don't know how this works, and so I'm pulling out all the functionality from the code here. So there's a lot of work with polynomials, and this stuff is done in kind of a weird way where my notes are kind of chicken scratch right now. I'm trying to figure out exactly what this thing is doing. It seems like we can take whatever the hell's going on here and combine it with whatever the hell's going on here, but this is just done earlier. So we're just stepping through and we're seeing what in the hell is going on. How are we creating this PWM style modulation? Now, FM and AM, I haven't looked at on the scope yet. There's different types of modulation that make the wave. So you can either do frequency modulation or you can do amplitude modulation. If you do amplitude modulation, that means that instead of going all the way high for a number of ticks, you would just go to the voltage level per that amount of time. I don't know what wave folding is. We're looking at wave folding right now. I don't know what it is. So far as I'm concerned, this is voodoo. But modulation 1 wavetable is equal to the mod 1 wavetable of I times mod. Why are we taking the previous one? I guess so we've created it there, and then we go down here, and then for mode is equal to 0, which is wavefold, we get our wavetable. The modulated wavetable is equal to the original wavetable times the mod number, which is 0 to 256, or sorry, 0 to 1024. 0 to 1024, but if our mod is the number 0, then our wavetable entry of I, of 0 to 256, is going to go from entry 0 to entry 1024, then it's going to go to entry 2048, but there's only 256 entries. What the hell? What is that supposed? Does it wrap around? But that's what our modulated wavetable supposedly becomes. So now that we have a modulated wavetable, we look at we slice it up. Mod WT. Then we go 0 to 256. What? What the fuck? Wait a minute. What is... I'm already... The entry mod wavetable of I is less than negative 512. Mod wavetable of I is greater than 1024 minus 512. What is going on here? For 0 to 256... Oh, I see. So everything is from 0 to 256. So for 0 to 256 mod wavetable I, so from then 0 to 256 of mod wavetable, I'm going to need that multiple times, greater than 511, and what was the symbol for and? or is vertical lines. I guess it's just ampersand, ampersand. So I'm going to do and. I'm just going to write and. There's also a symbol for it. Less than 1023 by plus 512. $10.23 plus 5, is it 11 or 12? 512. So greater than 511 and less than 1023 plus 512. Huh? But that's the value. That's the value. Mod wavetable of I equals 1024 minus mod 2. I think this is very confusing because it's wave folding, and I have no semblance of the logic of wave folding. Equals 1024 minus mod wavetable. I'm not going to use AI. No way I'm not going to use AI, because I don't know enough to know if the AI is lying to me. The AI will eventually lie to you, and I don't trust it. So this is the best way for me to figure this out, is just by making diagrams and absorbing some of this stuff. And I'm streaming it because it's kind of an important thing with programming. Not something I would commonly do, but plus 512. This one is minus 512, and the symbols are reversed. What the fuck? I guess these numbers can swing positive or negative. It just makes no sense that it would be constrained in the way that it is. So we're taking this, putting it here, but we're going less than negative 511. Mod wavetable less than negative 512. Whatever. The 511s and 512s are weird. I wish I knew the logic behind this, because I'm sure there is, but it's not explained. Greater than 1024, negative 1024 minus 512. Ugh, might as well just write it again. I thought this would be a little bit clearer when I did it this way, but it doesn't appear to be. Less than 512, greater than 511. So we're looking at the value of the modified wavetable. Yeah, this is like, this would overload that thing. I mean, like, how the hell would it even begin to reconcile? Because we're reverse engineering this right now. We're kind of figuring out what this code is supposed to be doing. And I don't even know how I would approach AI with that kind of a problem. Wavetable I is less than negative 1024 minus 512. So that's just this piece. So if it's both things, it does one thing. If it's only one thing, it does a different thing. But thing with the thing, thingy. This one is negative 1024 minus 1023. The 4s and the 3s are really getting annoying. Like, make up your mind. Mod 2 wavetable is equal to negative 1023. This one is positive 1023, minus, minus. This one's positive plus. So that would be mod 2 is equal to and this is 2048. 2048 plus, and the other one's 2047. It's negative 2047. Okay. Negative 2047 plus. It's like we're getting at it from two different sides of the number line is what I'm kind of seeing here. Minus 511. Or we got a 511 on Matthew Street. Negative 2047 plus mod wavetable of I, 2040. That's for wavetable is greater than 1023 plus 511. What is code 511 for municipality codes for police? Negative 1020. Oh, 2047. 2048 plus mod wavetable. 2047 plus plus. Negative 1023 minus mod wavetable. 1024. Greater than 10. Oh, greater than 1023. Oh, God. Okay, hold on. We'll get it there. We'll get there. Greater than 1023. This one's less than negative. I'm sure there's an order of these that would be a little bit easier to understand. That's why I'm going through this right now. What we're doing is we're making the mod 2 wavetable. Plus mod wavetable, 1023, 511. 1023 plus 511 minus 11. Okay, so those are all correct. And then the final one is just making it equal. Oops, mode 2. Hold on, well, I'm not being very space efficient with this. Mod 2 is equal to mod wavetable. Okay, so what is happening here? Copy the code, paste it in ChatGPT. It will not lie to you. You can try. You will lose nothing. I will lose my time, and I am currently spending my time figuring out what this code does. And I'm doing it by running through it and looking at what each individual thing is doing, and then doing some example numbers to see where it's going or not. This is the way to do it. It's losing my time on ChatGPT. If I paste this code into ChatGPT and I ask, hey, what is this code doing? I don't think I'm going to get anything like that. You're suggesting it to me, but like, I'm not going to waste my time doing that. You can try it if you want. I'm not going to get anything relevant from it, though, in my opinion. I would be shocked if it was able to give me a full rundown on exactly what the code is doing. That isn't just what somebody else said some other code was doing. So when we're greater than 511 and we are less than 1023 plus 512. Now, as far as I know, the entries in here are limited, but they are also being multiplied by mod. And mod can be 0 to 256, or is it 1024? So mod is dependent on mode. And so if we're in wavefolding mode, we are mode 0, and our mod is equal to the control voltage pot constrained to 0 to 1024 plus the control voltage input constrained to 0 to 1024, which is the ADC's limitations, and then the CV plot constrained from 0 to 1024, but we're just adding those two numbers together. So if my control voltage is at negative 5 volts and my pot is turned all the way down, we will achieve the number 0. However, if there's nothing plugged in, we will have 512 plus wherever that frequency pot is. So the frequency pot probably needs to be in a storage setting of all the way to the left, although you would think frequency pot would shift you in either direction. But what we're doing is we are folding the wave in order to create all of these things, all these different signals, and somehow that 0 to 1024 number is being taken at a bias of 3.6%, and then 0.9, so I guess an offset of 0.9, is then being added to it. So if we magically got 0 plus 0 somehow, 0 plus 0 times 0.0036 is 0, and our entry is now 0.9. And so from there, 0.9 would somehow be our reference to this mod table. So our mod is 0.9, and then we take that mod number, and what are we doing? So for the mod wavetable of I times 0.9 would be our minimum entry for wavefolding. So 0.9, so a 90% of whatever the wavetable value is then applied from entry 0 to 256 of mod wavetable. But wait, we're not using mod in any of this. We've generated mod wavetable. Where do we generate mod wavetable? We created, see, that's mod, not mod wavetable. Mod wavetable where'd that coming from? Let's check over here. That's right, it's made in one single step. Oh, it's made all the way up here. Oops. Right, so our wavetable times mod, that's right. Okay, so we're taking 90% of whatever the value of I of the wavetable is. And we're entering it into our mod 2 wavetable after we send it through this gauntlet of constraints. So what we're doing is we're creating, where was that? All the way up here. Wait, this one's for all. Oh no, that is just in this mode, rather. Okay, so just in this mode. So min is 0.9. So 0.9 is our minimum mod value. So whatever's in that wavetable, which we know what's in the wavetable, it's this thing here, and we just auto-generated it based on some of our settings instead of having this massive table. So wavetable of 0 is obviously going to equal 0, but if we're 0.9 and we're 0.004882 times 0.9, then the value of that's going to be 0.00439383, blah, 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 blah. So if our wavetable tells us that we are supposed to be at 3.7 volts, which is, approximately a battery, times 0.9, it's going to be 3.39. Okay, what is that supposed to do for us? I guess that shifts it a little bit in terms of that doesn't really shift, does that shift the frequency because it's moving through the table quicker? Possibly. And then after a certain value, of course, all of our things are equal to 0.6. Or sorry, they're all equal to 6. There's like a maximum that it can kind of like overrun into. So I don't understand what's going on with that. So that would be, for instance, 3.39 would be that entry in our mod wavetable, and that would be entry number, whatever number that thing was. And then we go from 0 to 256. From 0 to 256, we're looking up the entries from, so our modded wavetable, 0 to 256, if that value is less than 1023 plus 512, so it's less than, but it's greater than 511. So from 511 to 1023 plus 512, what is that affecting? What is that? Is that the PWM frequency that we're outputting? And what are those offsets? Where do those come from? They come from a resolution. Where does 512 come from? Greater than half of our resolution, less than half of our resolution? No. 512 and 512 is 1024, so I mean we're offsetting it by half. Why are we taking the values of that table that we have taken 0.9 of. So all of the entries of that table multiplied by, for instance, 0.9, it may be even more, that is multiplying up our frequency jumps so that at a certain point we are moving up amounts of frequency, and for other points we're moving down in those amounts of frequency. I think that's what's going on. I think it's adding energy and deleting energy. So like in a chunk from, where's our number line? Let's say it's negative 1024 to positive 1024. So negative 1024 all the way to positive 1024. And then we've got 0. Actually, 2048, right? What does that do? Wait, hold on. So let's just, okay, 2048. Negative to positive. And then we have 1024. 0, and then we have 5 12s. We got mid marks over there too. So that's our number line. And so from negative 10 to 2048, but then again, we're going from 0 to 256. So what the hell's going on here? 0 to 256, but we're looking at entry values. So for the mod wavetable entry values from 0 to 56, we look at whether or not it's above or below 5, maybe that should be a vertical axis, because we're doing steps, aren't we? Yeah, we're doing steps counting. This should probably be a vertical axis, but so if the value of the wavetable is greater than 511 and it's less than 1023 plus, so it'd be like here to here. Wait a minute. Here to here, because it is greater than 511 and it's less than 1023 plus 511. So we're in that portion there, 1024 minus mod wavetable. If we're in negative 512, negative 1024 to negative 512. So this is negative 512, 1024 minus 512. So that's here to here. It is 1024. Wait, is that right? No, I don't think that's right. Let's go look. Negative 1023 minus, okay. Minus WT. If it is less than negative 1024. Huh? Wait a minute. Less than negative 1024 minus 512. 1024 minus 512, so that's here and up. What did paint! MS Paint, you've betrayed me for the last time. So from here on, then it is 2048 plus mod wavetable. What? Let me double check that. Negative 1024 minus 511, and that would be, I'm just calling it WT in this example. And then at the end here we have, oh, it's supposed to be, wait, that's the wrong one. Okay, 2048 plus is up here. And and then below it is negative 2047 plus negative 2047 plus wavetable. And at 0 or below 512, which is everything else, it's just WT. That is somehow wavefolding. I don't understand it at all. But I guess what's going on here is this is going like this. By changing the frequency up and down. Or the, I guess the, well, it's not amplitude, but it's not frequency either. It's a wavefolding. I don't understand that at all. Somehow that goes through the Sallen key filter and creates our waveform, huh? I bet you that's explained somewhere, and I just don't really understand it at all. Wavefolding, PWM, Sallen key audio. Butterworth. Apparently Butterworth is the sweet spot for these things. Sallen key, TSC. This is just somebody asking a question about stuff. Folding. Not even in here. Cool, thanks, man. They didn't say wave folding wasn't included. Strange distortion, second order, Sallen key filter using LM358. Why is Sallen key second order? Blah, 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 blah. Third order, Mod Wiggler, that might be a good source. Oh no, this is just a different one. These are the exact same results I got from my other search, even though I changed it. Low bandpass filter, PWM Arduino, General Electronics. Somebody generate PWM 5 Nano for audio EQ from EV Blog. Trying to make some Sallen key filters for university project. Hopes making an EQ unit. I'm studying music technology and I'm a complete beginner with electronics. I have a few stupid questions. There's no such thing. Has anyone gotten any decent source about the construction of a working with Sallen key filters they would recommend? I've chosen some component values in the link below. Yeah, okay, so we were just asking about filters itself. The analog devices op-amp filter tutorials. That might be a juicy read. You can adjust the frequency of the Sallen key with a pot. This is common active in crossovers. Most graphic equalizers use gyrators. This is a much simpler approach than using active filters. The hell is a gyrator? Oh my god, I feel gyrated by this fucking thing. Look at how gyrational this thing is. Okay, so this is what we built for my EQ, for my my microphone EQ. It's just they're tuned to different frequencies with these capacitors, and they're used in order to make multiple bands that cover your frequency manipulation that you want to get out of the end of your thing. That's neat, but that's not really, it's not that his project is a lot different. Which, what synth has the most nasty, gnarly, and disgusting ... Yeah, all right. I can back that. That's a good question to ask. Triangle cores, bulk of 259. Nobody is talking about wave folding. Let me put that in quotes. We need wave folding because that's what we're doing. We're looking at right now, and I don't understand it. There aren't any great matches. Let's just do wave folding PWM. Aha! Something's very strange happens when I toy with it. Don't show that, you fucking ass. Why does it still show? Okay, I need to go into my settings here. Chrome undid a setting. Something very strange happens when I toy with pulse width modulation with a phenomenon I've noticed. Hearing wave-folded oscillators and low-pass filters. I don't understand. It's like word salad. I think it must be something. Let's go to old Reddit just so that I can actually read this thread. What is this? This view sucks. It's so bad. Why did they decide that this is good? Sitting there with Condé Nast, like, hey, what if we make it functionless? Stupid. Pulse width modulation phenomenon I've noticed when hearing wave-folded oscillators and low-pass filters, particularly Jupiter-style analog. I think it must be something to do with harmonics. Our brains are keyed to hear these kinds of harmonics from wasps and bugs. That specifically was done way before the IPO, but maybe it was to make it more attractive towards IPO. You make it more social. Everything has become a scrolling vertical thing. Phones have absolutely fucking ruined all of the progress we made in the 2000s. In the 2000s and the 2010s, we had all this progress towards people actually turning their phones 90 degrees in order to film something. But now, because everybody's on a phone, everybody's on a vertical screen, and so everything is filmed vertically. It sucks. We've regressed. And so this suffers from fucking phones. I think it must be something to do with harmonics, blah, 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 blah. Don't know what's going on. Are you Nick Pratt? Take a look at this plot. This isn't what I was talking about. This is friction. This is so far beyond. How come this is like the exact... I guess wave folding is something that they're talking about in the actual synth part. I'm looking for it in the like deep design stuff. And they like to use this word because they all know the definition of it, but we don't. And we're looking for the definition of it, but they're all just using it in conversation. Soon enough it'll be designed for Neuralink. I'm so positive about Elon Musk all of a sudden. I can't say a bad thing about him. Billionaires are not a blight on society. Tired of standard wave folding sounds. I have U-fold sworn by for about 2 years, and now when I patch it, I'm really not that excited about the sound. That's a U problem. I messed with DPO and verbose complex OSC. This is like beyond it. This is the people who use these. Is that Nanoland? No. These are the guys that use the sounds. I'm trying to make the sounds. Use one VCO to control audio rate crossfading between two other VCOs. That's the kind of weird stuff you can do with modular. So they keep talking about folding waveforms, and I don't know what it means. Everyone's a billionaire who's just a little bit down on their luck. We're all going to be billionaires one day. Believe me. That's how it happens. Number goes up. Number does not go down. Number does not stay the same. Number goes up. Bit crushing and wave folding control voltages. That's not what I'm looking for. Synths with wave folding in them. Waves folding sounds good, but limited for triangle waves. Huh. PWM and PWM wave folder. Hi, could PW and PWM be used for wave folding? I guess I'll click on it and just see. No replies. What in the hell is wave folding? Oh, Erica Synths. Here we are. Erica Synths explains stuff very well. They have a YouTube channel that is brilliant, and it does actually explain what the pieces of the circuit are doing. So I would expect that this would have kind of a nice write-up on it. It might all be hardware design, though. That's the problem. It's a YouTube video. Ah! I shouldn't just play his video. That's the problem. But there's probably some pretty good information in here. Although I think this is more in relation to how to use a wave folder. Yeah, patching strategies and building a fold. So this is not the electronics DIY. Although he does put one together. In fast forward mode. Oh yeah, he has that $500 oscilloscope module. He's getting a real oscilloscope for that money. Just get a real oscilloscope and some patch cables. This thing does not justify the cost. Anyway, okay, so that's not what we're looking for. It's possible that wave folding is not exactly what we're looking for. But nobody appears to have explained what the hell PWM wave folding is doing for us. So I actually don't know. Yeah, it's all in relation to synthesizers. Huh? Wave folding, an introduction. We found it. We finally found it. Somebody's going to actually explain it to us peasants. Oh, us poor dumb peons down here in the muck and mud, trying to make our way, paying our dues and living life humbly. We finally get somebody from on high descending to us, mucking through the filth and telling us what wave folding actually is. Download the wave folder objects and demo files here. Nah. Source code for the wave folder, wave stretcher, and wave cutter. Well, that's interesting. Pure data, blah, 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 blah. Maybe I do want to take a look at that. Okay, it opened up and then closed. Did we actually download it? Let's see. Is it in my downloads? Did I actually get a file out of this? Ah! I hate when you grab the window and it resizes. No, we did not. Save link as. Downloads. Save. A page on Stanford's website? Okay, these are Mac files, never mind. Wavefolding takes a ramp signal from 0 to 1 and converts it into an adjustable symmetry waveform. Yeah, there's some weird shenanigans going on, because what's happening here, and I should re-explain what's going on, everybody. We're trying to read through the code and figure out what's going on. Last stream, we figured out exactly how our hardware works and that it is working and that we're outputting the right stuff on the right things and we have our adjustments proper for the right frequencies. The 100K resistor thing that we did last week, I don't know if that was completely functional. I think we're doing just fine with what we have. There is a little bit of calculation and frequency stuff that we do probably need to do in order to figure out if all of our stuff is exactly rightly tuned, but the hardware layout that we have right now in CAD is correct. That's the important part of last stream. So this stream, what we're doing is we're going through the code and we're figuring out how this device, this voltage controlled oscillator, turns pulse width modulation signals into waves. And there's a couple different techniques for that. If you would like to know more, this entire project started, this entire project started from a fellow named Hagiwo, or personally named, they named themselves Hagiwo. They are a YouTuber and they create affordable modular synthesizer circuits. That means like $10, $20, right? You can put together a nice digital circuit and it will do all the functions of a digital circuit in a modular Euro rack, right? And so I like this. I like that it's not expensive. It requires a little bit of elbow grease from us in order to get this into our English-speaking style, and for me to be okay with this software and able to manipulate this software. What I see in this circuit here is I see potential, because what this does is this takes a PWM output and a bunch of modular synthesizer inputs, and it uses a $5 microcontroller, an RP2040, which is 133 megahertz. That's fast. That is very fast. So you get this cheap, fast, easy to program microcontroller, and you throw it into the modular synthesizer. That can do just about anything. Whatever we can do software-wise. Problem is, I don't know shit about how this stuff works. And so I am new. I didn't know what the Allen key filter was until last week. But knowing how a Allen key filter responds to a high-frequency PWM input and how to manipulate that in the Raspberry Pi is going to turn extremely powerful in terms of like what I can build synthesizer-wise. What basically is happening is explained. Oops, sorry, that's the wrong window. What is happening is being explained by Xiao, which is linked in the Hagiwo solder state article about the RP2040 Eurorack modular synthesizer. It's a $9 Raspberry Pi VCO, right? And so Hagiwo links over to Xiao's stuff, and there's some calculations that we can look at. The way that a microcontroller works is you have a clock that is doing ticks, and every time there's a tick, something new happens. It's like a piece of clockwork, but instead you have a bunch of punch cards with holes in it that'll tell this piece of clockwork what instruction to perform. And instructions can be move data to here, put this into the math processor, put this over here, take this part of the data and put it here. That's essentially what programming boils down to. So while you're thinking about it in that terms, you can think of the pulse width modulation output of the microcontroller as dictated by that clockwork. And that clockwork is running through ticks of time and determining whether or not that pulse width modulated signal should be a 1 or a 0. Since it's pulse width modulated, the width of the pulses changes back and forth over time. And so if you change how much that moves back and forth over time, you vary the amount of positive and negative elements this filter sees within a given period of time. So you tune all your values to that, and what you can do is have your PWM signal essentially playing Flappy Bird. You can think of it as Flappy Bird. When you add a little bit more voltage to that filter, it'll go up, and then it'll start to drop down as it's negative. As it's positive, it goes up, and then it's a little bit more negative, right? It's Flappy Bird. You're playing Flappy Bird. Only this time you can hold the button down, and the bird will keep going up and up and up to a theoretical maximum of whatever your voltage supply is. So what we're doing is we're hitting that button longer and longer, and that is keeping our Flappy Bird higher and higher up, and it is approximating this waveform as much as possible. And so we are able to, with a couple different modulation methods for this pulse width signal, make this go high and low. So it's not only the amount of time that you hold your hand down on the button. What you can also do is you can hit the button a little bit less. So you can actually modulate, where is that? You can actually modulate it using amplitude as well. So what you would do is you would hold it down for a certain voltage level over the same period of time. And that would also have the same effect of affecting our Flappy Bird level up and down. So you would give it less of a positive or more of a positive. You get maybe a slightly smoother waveform. I hope that breaks it down properly so that you guys can understand what's going on. When we get to wave folding, I have absolutely no idea what the hell is going on. I do not know what is going on in wave folding. And so wave folding is something that I would like to learn about, because we're looking at it right now and it makes absolutely no sense to me. Yeah, choppy boy to wiggly boy. There you go. You are now a genius. People that bother, you're such a genius. No, I'm not. No, I don't understand any of this shit that I'm talking about. I had to relate it to Flappy Bird in order to have any idea of what I'm doing. That should tell you. We should have, like, I should be writing, I should get a big piece of glass and put it right here and then write all the equations as I'm going. But then you guys would see them backwards and that wouldn't really work out. Do like a Khan Academy thing where I put all my notes and they're just up on top of me. Of course, that would eventually just look like, that would just look like this in the end. I'd be like, I don't know what's going on. I don't know anything. None of this stuff makes any sense. And I've been making it up this whole time and hoping nobody calls me out. I don't know what to do. It's the whole house of cards is falling down, and oh, I figured it out. So PWM Raspberry Pi bare metal, we don't need that. And this is doing kind of simplistic things. I don't know if the wave folding is supposed to be a triangle wave. The modulation, when you send like a radio signal out and you take your audio and you send it out over the air, your audio exists as a waveform, like a normal voltage waveform. If I put that waveform into an antenna, it wouldn't really do anything, right? It wouldn't really do all that much. But we've discovered that the relationship between electromagnetism and antennas and radio waves, we kind of know a lot about that. What we've discovered is if you are amplitude modulating something, you can take the waveform of your voice, and depending on the voltage level of that waveform, you can apply a fixed frequency but multiple different strengths. And so you have a signal that's going rah, 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 right, as your voice waves up and down. And so if you apply, you modulate your voice over that signal. If you do frequency modulation, you can take the level of the waveform of your voice and apply a frequency to it. So it goes right, at a very high frequency. And if you apply that to an antenna, you now suddenly have the ability to transmit that waveform, get it back at another location, and if you reapply that frequency, you can unmodulate it and produce audio out the other end, right? That's radio waves. So in the same sense, we are taking this high voltage, or high frequency, it's a very fast PWM signal, and we are then unmodulating it by applying a filter to the end. So we have that Salin filter that works like Flappy Bird, and we're applying that high frequency filter to that. I hope that breaks it down in terms that you guys understand. If I had visual aids, I've been trying to use as many visual aids as I can, but if we look at what we actually have here, a failure to communicate, what I can do is actually put the scope up on the screen. I can poke this thing at the audio output, the PWM output, and we can see that we have roughly what is in the examples. So if we take a mathematical representation of the waveform and we do the business, oops, that's the offset. Why do I always go to the wrong, I like go for the knob and it's just the wrong one. It's always the wrong one. So if we take our waveform mathematically and we change that into a amount of PWM, we can then recreate the waveform on the other end. And so that's the math that we've been going through today. So this is complicated. This is very engineering. This takes a couple levels of math and science in order to understand, but ultimately I think it is very important to show because it's cool, and you could do stuff like this and you can show how cool it is. Oh, and keep in mind our the signal is being applied to an inverting amplifier. So in this case, the more low it is, the more high it becomes, because we're inverting our signal on the output, which is okay because it's a waveform. It's just going back and forth. We don't need to be frequency specific or voltage level specific. So because we have an inverting amplifier, you can see where the signal drops off and becomes more negative, we are actually the most positive. If I go over here and we look at this, we can see where it becomes the most negative, we are the most positive. I just touched the screen and set it to 0 by accident. But how cool is that? I think that's really cool. I think you guys are dumb. Stupid and dumb. I'm going to see if I can clip onto that lead and maybe we can have a more permanent representation of that PWM for our example here. Because I guess I can try to like run some numbers if I need to. So we need a scope hat. And then I'm going to take this wire because we've already got a ground connection, and I will clip into this part here. I can put this aside. I'll power down so I don't blow anything up when I'm doing this. I need to take that second to bottom pin with this little hook here. Oh, I can actually go from out here. It'll pop off more easily, but that's a nice stable connection up top. These pins overshoot a little bit and they stick out of the top of the micro, so that's a great place for you to clip onto them. I could probably clip onto them with the big clip, but that has a little bit of weight to it. I want to keep this nice and light. I could have done this with the power on. Oh, I apparently did do it. Oh, because I still have the USB was still plugged in, so. All right, there we go. Cool. Look at that. So I'm trying to learn a bit more about how we do this. Oh, did I knock it free? Trying to learn a little bit more about how we do this. And wave folding, I don't think I've implemented wave folding. I don't think that's what we have going on right now. I think I just took the frequency modulation and I plugged it in. So it's going to be a little easier for us to interpret frequency modulation. In terms of like wave folding modulation, I have no idea how it works. I do not know what's going on there. Maybe that's producing a triangle wave in the end, but I just don't know. Like, what in the world is going on with this stuff? So we've got this Wave Folding 101 article. Wave folding takes a ramp signal from 0 to 1, and I guess that's what that 0.9 is, converts it to an adjustable symmetry waveform. This is based on a threshold where any portion of the ramp that falls below the threshold becomes the rising part of the waveform. So this is how you make some weird stuff. Triangle man hates person man. They have a fight. Triangle wins. Triangle man. The triangle wave is used to modulate the sine wave. Huh. This isn't even getting into the one that totally breaks my brain, where there's multiple sine wave things going on in different frequency modulation schemes. The phasor output in red. That's what Stanford says? Okay. So we're this may pertain to what Xiao is talking about with this stuff. If you want to do it seriously, you should prepare a wavetable with the alias noise countermeasures. Maybe that's what the wavetable was for. Wavetable with the alias noise countermeasures. Since I'm not concerned with the sound quality this time, I won't do that, and we'll generate a waveform with the following definition. The horizontal axis phi and the vertical axis is y. I'm calling that phi, I don't care what it is. So that's just a simple statement. Phi is equal to y. Starts at 0, increases time. Maybe this is not what he's talking about. You make the steps smaller, you get... Huh. Noise in the waveform, but the random numbers used in the noise are generated using RP24 to use hardware random number generator. This is different. This is a different project. No, I guess that's not what he's talking about. Sampling rate must be set in any case. You'll need to redo the conversion or quantization. Pico Extras has PWM audio. There's a slightly functional library call, which includes functions such as sampling rate conversion and dithering using an interpolator. Yeah, I don't know. We haven't made it very far today. We're not very far into this research. The green phasor output. All extremes threshold settings of the wave become either a ramp waveform in the output phase or sawtooth. Since the phasor output signal from 0 to 1, a bipolar switch is used. What the fuck? Standard range of audio signal may be disabled. Waveform used. So wavefolding is a little bit more complicated than I thought. The symmetry can be controlled by any audio signal using a sine wave to modulate the wave shape. Here we go, Chester. Using a sine wave to modulate the wave shape. Much like traditional FM's frequency modulated synthesis, the relationship between the fundamental frequency and the modulator, the carrier to modulator ratio, CMR, determines the harmonic or Jesus Christ. For example, CMR of 4 results in a steady, unchanging timbre. And okay, so this is like a complicated waveform. This is kind of crazy. Feels like a noise gate, but smarter. Baseline plus or minus the modulator exceeds -1 to 1 range. The modulation is clipped. Portions of the waveform become hard saw ramp sections. What the fuck? Audio rate modulation and pulse threshold. It's like letting your synthesizer have some clipping just for fun. The waveform signal has another threshold applied to it so that any signal above or below the threshold is converted to a plus or a minus value. If no audio modulation is applied to the wave shape, then the result is similar to PWM, but with the modulated wave shape in a non-integer carrier to modulation ratio, there's a complex evolving timbre generated. Timbre! As with all the techniques described here, the control signal is at audio rate, and any modulator such as low frequency oscillator or any other audio signal may be used to modulate the threshold. What the fuck? Even with modulating the pulse threshold, the evolving timbre created using the non-integer CMR carrier to modulator ratio generates timbres that share the complexity of the wave folded signal, but with more extreme jumps in timbre. Note that the graph above, the pulse threshold modulated output, is scaled to 80% for better graphic representation. I still don't get what I'm looking at. That's wave stretching. We're not worried about wave stretching right now. Wave folding seems very, very complicated. I don't quite understand it. I have a basis of understanding it, at least. I have my notes. But this isn't wave folding. I was looking at whatever this thing was outputting. It doesn't look like it's not creating a sine wave. It's doing something more insidious. It's like making a weird folded thing with the PWM, like something weird like that. That's something I'll have to look at later, because I just don't understand it right now. Too dumb. Oh man, you just missed a whole bunch of weird stuff about waveform, like modulation and stuff. The Here, I'll link this article, but I don't understand it at all. What just happened? No. Don't inspect source. Get out of here. I also don't feel like learning this right now. Yeah, exactly. You don't feel like learning it and teaching it to the streamer. I have absolutely no idea what the fuck is going on. I like it's crazy. It's stuff I understand. I understand modulation. I understand manipulating waveforms and stuff. It's just we're talking about like a very specific thing, and it's strange. I understand frequency and amplitude modulation though, and I think those are a little bit simpler in this code. So we're still going through code. We're still trying to learn how this thing is doing the job that it's doing, because I didn't have time to do research last night. I did a little bit, but going through this line by line and just jotting down notes on exactly how it's working are actually helping me quite a bit. I've got a sense of what this thing is doing, right? I got a bit of a sense of what this thing is doing, but I don't know about the threshold, et cetera, et cetera, et cetera. Friday night, having other brain power left. Yeah, exactly. It doesn't matter. It's okay. I don't need your help chatting. I can keep sustaining on my own. So let's continue on with our code and figure out what the hell is happening in this thing. So wavefold, FM, and then down here is AM. AM looks dead simple, amplitude modifying, but let's take a look at what happens with frequency modulation. Now, frequency modulation has modes. So mode 0, mode 1, and mode 2. Has 8 submodes. And in these, it's mod 2 wavetable. So the mod 2 everything is okay. Mod 2 wavetable is equal to. Now here's where things get hinky. I have gone through these equations, and down here at the bottom of my other code, I have all the equations busted out into polynomials. Here comes the nomial and the polynomial part of the stream. Don't be scared, don't run away. Everybody's run away. Nobody likes me doing math. Holy shit. I have 30 viewers. Wonderful. Doing shit like this is not going to get you viewers. Anyway, I do it for the love of the game. Yeah, all right, let's go over to here. This means I definitely should not be doing math on the stream from now on. I've proven it out. I've discovered that Twitch is allergic to math. Also that everybody's probably busy this Friday, but I doubt it. I think people looked at, I'd rather watch Dragon's Dogma. I've taken all these equations and I put them down into like a pseudo function that sort of splits off all the different things that are going on in these different FM modulation systems, and it's all a function of sine. It's all a function of a sine wave, and some of them have additional things, some of them have less things. It's a very strange setup here. This one has an additional polynomial inside of it that we're going to have to figure out. So this is going to get a little messy. But what's going to happen here is we will just start putting these things together. Because, I mean, look, like this right here is actually this. And then first and second, I thought I'd split it off into a polynomial kind of thing. Let me go get the original equation from whatever that first piece of the sine wave is. And that's going to be in the other code. This is the functional code. I'd rather actually do work I'm being paid for. I'm sorry. I'm so sorry. These are all the same. Okay, so how are we going to do this? It's 2 elements on this thing. 2 polynomials. Sine blank times blank. Actually, there's more to it than that. 2 m pi I over 256 plus mod divided by 128. What in the world? How do I even split that out? That's strange. 250, let's say, plus. So, all right. Parentheses, exponent, multiply, divide, pemda. So we would be doing all of the elements in between the pluses first. So 2 m pi. So let's do, okay, this is going to be tough to get into my notes. So sine and then we're going to have this big thing over here. So it's 2 times pi times I over 256. 2 pi I over 256. And I guess we could do 2 pi I over 256. Plus mod over 128. It seems like we're weighting things. 2 pi I equals a full circle mapped to 256. What's up, RYG? How you doing? So we are taking 2 pi I, which is a full circle mapped to 8 bits, and then we're taking a scale of that. Mod over 128 and 256. Because, I mean, we're making, okay, so we're frequency modulating, and we're taking a number of frequencies that go around a circle, right? Well, let's see how far we get with this, and maybe I'll understand it more. In this case, 256 is the number of entries in the wavetable, so the sine wave fits perfectly in it without mod. Plus part shifts the phase, so we're not done yet. Entries. Circle. Actually, it's circle over entries, but all right, entries per circle, and then we shift the phase over. That's the first couple things, but now we're doing another sine. That's over 256, and then we multiply the end result by 511. So we do, for the first one, we do that, but then there's other polynomials that come into play for the other signals. And what I'm trying to do is relate them to one big equation and then have polynomials that can be canceled out with default settings, so that when I call in this function, I can call in the number of things that needs to happen. So I'm trying to write it down so that I understand this a little better, and I break it up into modular sections that can be altered later. So plus mod 128, that's all the same. And then here we're multiplying it by a thing. But then the parentheses get a little bit whack. We have different numbers of stuff. Actually, you can ignore this one. This is me trying to reproduce it, and I just made it a little bit more confusing to look at. These are all in Hagiwo's code. They're in Hagiwo's code, and you can cut and paste them out of where they are and work with them if you want, but I wouldn't suggest it. It's too confusing. See, this one has parentheses around this specific area, which is why I wanted to rewrite this, because there's like variations in everything that's going on here. This is going to get very sloppy. The end result is multiplied by 511. I guess I can reverse those and do 511 times. Wavetable storing values between negative 512 and positive 511. And so everything is scaled from negative 1 to 1 up to that range by multiplying it by 511. So this scales Ah. Everything is scaled from -1 to 1 and 2. To negative. Wait, it's the opposite way around. Scaled from -1 to 1 up to that range by multiplying it. No, it is, yeah, that brings it to the 1023 values. But that is the reason why we're multiplying everything by 511. So sine, the output from sine is from 0 to 1. From 0 to 1, is that right? I guess right. But yeah, now I need to make heads or tails of all of these different equations coming together. And I forget my transitive property. I don't even know if these parentheses line up to anything. If I highlight that, am I going to get another one over here? It should be highlighting the other parenthesis. I don't know why. Oh, maybe because it's commented out. That's easier to read anyway. Yeah, so that caps the whole thing. This one caps the first parenthesis. So we're still inside of the sine function. And so sine 2 pi m3 over 2. So then we've got another one of these, and we're multiplying it by. So I guess, should we take the whole front and multiply it? It's like, unless we're multiplying mod over 128 times sine. Mod 128 sine 2 pi I. I is the, what is I is the number from 0 to 256. Times 3. Oh, times a variable. So times, let's just make that 2 pi I. Are we 2 pi I times variable over? I guess we'll probably do it that way. So it's, oh wait, it's 2 pi times x times I. Oh boy. I gotta write this in the same way, otherwise it's gonna like 2 pi. What do we call the variable? Oh, is it v1 or maybe just a, b, c, and d? I don't know. A times I. 2 pi a times I over 256. I don't like that. I don't like that notation. 2 pi ai. What should that look like? And if I keep doing it like this, that just means I need to add that. So if I do that, then it'll be... I've done math before. It's not a long time. A over 256. And then that's it for that one. So we've got this whole thing in order to shift the phase. And in the instance of the first one, that's number is 3, then it moves to 5, then 9, and 11, 17, 19. So I guess it's scaling it in some way. But then our next one is the same thing, except we've got another polynomial in here. And it's mod 128. So the second one is plus mod. Oh God, that's so sloppy. My writing is getting terrible. Mod over 128 sine. Sine. Two pi 3 I 256. So it's pretty much the same thing, but it's another 3 value. 2 pi I over 256. See, what I'd like to do is pull these out, these polynomials out. So 3 and 3, 3 and 3, 5 and 7, 9 and 5. Okay, so they need to be different values. 2 pi I b over 256. Now that doesn't activate or deactivate it, huh? Yeah, FM mod is dictated by mode 1. 0 to 1024 to 0 to 1024, then constrain it from 0 to 1024, and then divide it by 8. So it becomes 0 to 128. So when it becomes 0 to 128 in FM mode, it's divided by 128. So it'll be 1 over 1. What happens in the microcontroller when you do 0 over? Because that may be the way that I can cancel out these, but no, that won't. Well, that'll make this a 0, and then it'll add 0 to it. So if I 0 it out, then mod would equal to 0. But 0 over a number, I don't know what the microcontroller does with that. So yeah, we've got another polynomial that we've identified from the second one. Onto the third one, I think that's just a value shift. Just a value shift. Although there's an extra parenthesis in there that I'm wondering about. So we're parenthesizing the whole thing. We're always parenthesizing the whole thing. Okay. I'm already working around the clock. What are the extra ones doing? We've got that sign there. This one next to it goes to here. No, it's the same number of parentheses. I don't know where this, I guess that's just coming from having that second polynomial in there. Okay, so we've got one polynomial, we've got two polynomials. Then we jump to this hedonistic shit show. What is this going on here? This one adds a polynomial 2 sine m pi 9i 386, 368. This one adds one in between, like splits it up into two different factors. Maybe that's what's going on. So what happens if I take that and I bring this, well, if I bring all these in, or I bring this one out, because this one has a sign there, but it doesn't have a mod over 128. It does here, mod over 128, but then we're adding to it another sign, which exists in its own little microcosm. Okay, it's still inside the main thing, but it is sign of that stuff without this stuff plus that stuff. Oh, my head. Okay, hold on. I'll figure this out. So it's 1 to 1, and so it would be like a selection. Like this is one version. Then we would do all have that, all have the phase shift. Yeah. All of them have that. Then the mod 128 is in 2, 3, this would be FM1, FM2, FM3, FM4. So 2, 3, and 4. I guess they all have that. All except for the first one. all but number 1. Then what's going on out here? I arranged it just visually because it's mod over 128, but then this adds like a whole thing to it. So it seems like these are actually way out here. Like this. And they just don't have a lot going on. They jump into the second set of polynomial equations. I got to figure out what's going on with that interstitial one too. It seems as though that one is a little bit further in. Like if I take this one down to where there's mod over 128, it's a little bit long. What if I compact this down a little bit? So now everybody gets along, sort of. This one has a little bit of extra baggage going on. Yeah, that kind of looks right, right? Of course, this one has an extra parenthesis in there. What's that coming from? It comes from that sign. So that sign's adding an extra thing to everybody. But it's still mod over 128 times sine of all this stuff. And that has 2 things in it, and this one only has 1. It kind of seems like that one should be all the way out there, and this one's like an extra one on this specific instance. Kind of weird, I know, but... Yeah, I know. Sine of sine of sine of sine of sine. I think if we're looking at this as adding polynomials, this should probably be organized like this. And then I take the end piece and I bring it all the way out. So take the end piece, bring that all the way out, get rid of those extra spaces. Where were those extra spaces? Whatever, that's fine. And then this all the way out. I'm starting to see it a little bit more. I'm starting to see what's supposed to be happening here, and it's kind of in line with what I was thinking of before, which is you have polynomials and you cancel out the polynomials in order to create a master equation that has everything that you need in it. So like the divided by 2 times 5, 12 and stuff like that. Unfortunately, I could align it all and bring all this stuff all the way out over here, but it's still. Sin City, huh? This one's kind of tough because there's not room for it. And then these would move out even further because we have another plus here. Wait, there's no parentheses on that one. That doesn't just end there. You add a mod into that specific one. So this would have 2. Bringing this all the way out over to this. Hold on, let me cook. I'm cooking. I can cook. I know how to cook. And then we actually need this one all the way back here. Actually, wait, what's going on? Okay, we need that one. Yeah, okay, wait, this one comes out to here. And then this one. Is that right? I'm just looking at whatever is associated with the first sine wave. Be like that. I don't know. I mean, I know these have an extra one on them, but just try to line stuff up because I think that'll help me think about it in better terms. Oh God, I need this one all the way back there. Rewind, rewind, rewind. When I can't do it with math know-how, I'm going to do it with organization in programming. Oops. Look, all this calcs would slow the microcontroller way down, but using an RP2040. Yeah, it's running at 133 megahertz. The thing is already screaming fast. Screaming fast. It's crazy. It's got all the speed. Does that make any sense? We have this here capping off the entire thing, whereas we have this here. We have two capping off the whole thing. This one's capping off that. And then those two are the internal coefficients there. And then the one wrapping the whole sine wave? No, that one's wrapping that. It's that. The calcs are required to do FM modulation properly. What's crazy is all this is running on one of the two available cores. I mean, this has loop 1 and loop 2. So technically, if you figure out how to do multiple cores on an RP2040 and Arduino, you could split one of the cores off to do all the modulation, because that's how the original works. But it's so fast that it just doesn't, like, yeah, it just doesn't need it. I'm trying to make heads or tails of this because they seem to follow like a common, you know, this is a canceled off polynomial. Sorry, a nomial in our polynomial, a singular nomial that is canceled out in certain modes. So as we roll through, we don't have certain polynomials inside the parentheses. We have other ones that are added outside the parentheses and they take a standard form. So what I'm trying to do is peel off all of these standard forms and figure out what the hell's going on here. Like this should probably get a tab because this is the one that caps off the entire function. Let's see, we've got a divided by 2 snuck in there. How do we cancel out and uncancel out a divided by 2 inside of our thing? That should get closer. And then we have this one, which is capping off that. But then this one caps off the same thing. So that one needs to be in line with everybody else. And what is this one capping off? That caps off the sine wave. So does that one, and that one. But then these are for the additional coefficients. So these need to go out. And this comes back in. This is literally just visually representing all of the different polynomials here. And it is helping me quite a bit, to be honest. So yeah, okay, so now what we have is we have for the first one, we have 2 pi I over 256 plus mod over 128 sine 2 pi a over 256. Now you could write that a bunch of different ways. I'm just writing it in a bit of a compact way. You know, I'm just taking the multiplication and I'm putting it up on the whatever you call it. Yeah, this is the new they simplified things a lot. They took that Fusion 360 approach and they made it very simple looking. So you can pretty much do whatever you want with it. And it's really good at calculations. And then what we did is down here when we were done our calculations, we took a spaceship up to the upper part over here where we continue them on. It's very functional. This is my CAD program. It's very hard to write clearly in this program, and you know, because I'm using the mouse. So plus mod over 128 sine 2 pi I times 3 I over, so this times number pi over 256. Now that changes, so we'll put that to another variable. I don't know how I'm going to organize all these variables, to be honest, because I wanted to make them into a function, but if they're going to be different variables for all these things, and I still have to cancel out entire polynomials, I mean, I guess I could have I don't know what I would do. In order to cancel out a piece of the polynomial, I'm not sure. I mean, maybe I could calculate them all out separately. I could do each individual polynomial, and if it's set to like -1 from the calling of the program, then it would just cancel it out, because none of these are -1. Why is it going up and to the right? What's going on here? Is this just the way my mouse is moving? I can't continue this on. This is going to go in a big spiral until I'm done doing this equation. We'll go down a line. Do you hide numbers in your beard? No, but I find them there. Thank you guys for sticking with, you know, shitty calculation, because this is not what we do here. We usually do this kind of stuff. But every now and then, the engineering sneaks up on you, and you're forced to do some actual calculations. I can't tweak the knob and have anything happen right now, because this is just a very rudimentary program that we've got running here. But you can see the concept of what we're trying to do here. As we modulate these PWM values, they play a game of Flappy Bird with the voltage level. As they play that game of Flappy Bird with the voltage level, we end up getting a voltage level that represents a audio wave. An audio wave. You get what I mean. So our next nomial in this polynomial, this polynomial, mod 128, it's taking a form that we've never seen before. Never have we seen this form before. It's so unique and new. Oh wait, that's not the right one. Totally and completely unique and new. This one will be C. That's the worst C that I've ever drawn. I'm just gonna pull another one in just because I'm crazy. And then that's yeah, so this one is D. C and D is plus, and then this one is so it's all but number 1, 2, 3, 4, 5. Mode number 2, 3, 4, 5. This one's 6. And then, do we finish this off? Are we done with this polynomial? Yes. That is the end, my friend. Except, how do these match this? I feel like there aren't enough parentheses. This one should definitely have an extra one because it's got this thing there, but then these don't. What do these have that the other one doesn't? No, they're the same thing. This should close off the end of that thing. Okay, yeah, but not the whole thing. Whereas this closes off the whole thing? No, that closes off that thing. So this is actually sine of that. Oh, sine within a sine. Oh, wait a minute. No, but those are all sines within sines. Repeating. Cells within cells. Am I going crazy? I think I'm going crazy. There's an A, there's a B. Oh, 256 and 124 on some of them. So that would be... So the ones, these are all 128. These are all 256. Those are all 2. 2 pi I, 256, 128. Those don't change. So those numbers will stay the same. 2 pi I, 256, mod over 128, sine 2 pi blank I, 2 pi AI over 256, 124. So that's going to be A or B. It's just basically scaling it, I guess. We'll make that A1. Over A1 and then probably B1, right? So then it's over 2 pi 128 times sine 2 pi blah, 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 A over A1. And then we're adding before the parentheses. Oh. 128, 256. Some of them have a weird scale. But we're actually before the parentheses on these. So I did not do that right. So we got to look at that. A over 256. Sine. Okay, hold on. 256. And then that's the end of that one. But there's no parenthesis here. So it's mod thing plus thing. Does the math library not have an M2 pi? I don't think I've tried to compile with that yet. Oh, it reduces it? Polynomial long division. God, this is all of the hell of middle school is coming back to me. Sine of a sine of a sine of a sine. I saw the sine. It opened up my eyes. I saw the sine. Without understanding, I saw the sign. It opened up my eyes. I saw the sign. My understanding of this is getting less and less as time goes on. It's starting to dwindle slowly with my mental faculties. If I was smart enough to make a constant out of 2 pi x, I don't know. 3.14159 So apparently these signs are all internal to one another. But is the sign is expressed within itself if it's the end, my friend? Because like these are the ends of all these, that's the end of all those. Then we have the end of all the multi-polynomials. There's probably a better way for me to represent this, to be honest. Probably a slightly better way for me to represent all this stuff that's going on and what's inside what loops. Because that sign ends the whole thing. This one is an add-on. So no matter what, they're all adding on to one another. But are they, wait, but are they nested? What's going on here? This sign ends all the way out here. This sign still ends all the way out here. This sign ends all the way, no, this sign ends halfway through. So that's the difference. This one is missing a ton of polynomials on it. Because if I'm ending this one where the other one ends, then this is going to go way out here. That screws up my whole thing. That screws up my whole layout. It's so weird. I wanted to organize it. And then this sign ends same spot. It ends over here. So this stuff is like way out on the fringe of the equation. And this stuff I'd have to bump all the way to the end to make it match up. How annoying. All right, so let's take it piece by piece. Let's just figure out what's going on here. So the first one is just that. The second one is all but one. then there's no parentheses. Okay, so first and second one. So, right, first sign ends here, right before the 511, whereas the second one ends inside of that. The second one ends, there's another parenthesis for another sign in there. So it's sign of sign of sign of sign. This one is sign of sign of sign. There's another one in there. So it's 1, 2, 3. So the maximum number we have inside of this one sine wave is 4. So potentially 4 nested sine waves. 1, 2, 3, 4 on the screen right now. And then we need to check the denominators of the 2 pi I parts to see if they all need to be variables. So what that becomes is essentially, okay, so it's sine, I hate saying sine so much, 2 pi I over 256 plus mod over 128 sine 2 pi I times A over A1. I'm not going to have room to write this. Let me just go down here, move over a little bit. This is breaking my brain. So sine 2 pi I over 256 plus mod over 128 sine 2 pi I A over, damn it, over A1, A over A1, plus mod over 128. Sorry, yeah, mod over, does mod over change? Hold on. Mod over 128, mod over 128. Holy shit, what's going on out here? Mod 2m pi. Mod over 128, mod over 128. So it's always mod over 128. Always mod over 128. This is getting crazy. So far, this is as far as we know. Mod over 128. Ah, that's not the right numbers at all. 1 to 3 is 3 layers. Hold on. Let me cook. Mod over 128 sine 2 pi A, 2 pi I B over B1 A, B, C, and D, okay? I'm just going to start stealing my coefficients here. I don't have room for this. Hold on, I have infinite room. This is MS Paint. Come on, give me some background there, buddy. Okay, this file's getting huge because it's literally just my scratch notes. A, B, C, and D. This eraser is very ineffective. I didn't even change the size of the eraser. What the heck? Fine, whatever. Funky selection. So this is C, C1, D, D1, And then we have a bunch of parentheses to cancel this out. So first sign, second sign, third sign, and then the last 1, 2, 3. So 1, 2, 3, 1, 2, 3, 4. Then we have the stuff that's outside of it. So this is all of them, and then the rest of them are some of them. So we need to somehow cancel out mod over 128 times sine 2 pi ID over d1. Whew. You get a computer-generated algorithm. Yeah, I mean, GPT is a solution in search of a problem at this point. Stuff like this, I don't really think it's the silver bullet for. So let's just blow all this stuff away. And this is what we have so far. So we've got 511 times bless this mess. So 511 times, and we got this whole business here. Should rotate it a bit. My writing seems to trend upwards. So it's this nested sine wave, and I guess that's getting into like, is it getting into how like multi-frequencies are coming in? I don't know. Graph them on GeorgeBra. I don't even know what that is. A compiler can take away constants and turn them into one number to use final code. That's why instructors tend to encourage keeping whole equations in your code. I don't like that. I'd rather split this up into multiple lines if I was going to do that. You could do like individual calculation of multiple lines, and then you could have a value that defaults into making it into 0, or making it into 1, depending on what you're doing to it. Yeah, this nitty-gritty stuff, this reverse engineering stuff, I do not think it would do a good job in. But now we have the stuff that's outside of our main mess of nested sine equations. How many? Wait. 1, 2. I think, yeah, that's 4, right? So it's 1, 2, 3. And then this one has this tiny little 4 on the end. And then outside of these parentheses, we have this stuff. What is it? What? I think that one's doing the same thing. I just haven't moved it with the rest of them. Where does that one end up? That one closes off that. This one closes off. Yeah, the same thing. Okay, so yeah, this is the same thing. So now we're all the way out here. Wait a minute, what's all this white space? I don't need this. This isn't necessary. Actually, wait, well, no, this white space is not necessary, but the 511s should be with the other 511s. Whatever, who cares? Let's just keep working with the example. So then, what are we dividing by 2 on this one? We're dividing everyone by 2. So, oh boy. So this will have to be like a 1/2 coefficient somewhere. And that's multiplying it's dividing everything by 2, and then so 1/2 of this one. Only FM, what is it, 8? Jeez, this is so weird. Welcome to wave folding, where everything sucks. Everything sucks and the equations are impossible to understand. We'll get through it. So sine, and then are we nesting the sines? Yes, we are. Yes, we are. So we've got a double nested sine wave, and this one has its own unique parameters. Mod over 128 still. This is mod pi times something I. Now, are we doing that all the way at the beginning here? 2m pi I. So this is not, that does not change for those, but this second coefficient does. And then in this one, we divide it by 2. So we're going to have an A and an A1, a B, a B1, a C, C1. We'll just keep going down in letters here. So that is plus, so plus, we have the same thing over again. 2m pi 9 times I, 2m pi, so sine, so we're going right into the sine wave here. So this next one is sine. I feel like sine has lost all meaning. I don't think I think I've reached semantic satiation at this point. The semantics have been satiated. 2 pi, what were we on? We're on E. 2 pi E I. 2 pi I E. A over E1 plus, and again and again, sine, oh, mod 128 sine, mod over 128 sine. I'm just glad there's a fixed number of coefficients on the ends of these. Mod over 128 times sine 2 pi, 2m pi times 2 pi I f over 1. Speaking of AI, using Excel to manage F1 teams now. Did you know that? What a wonderful program Microsoft Excel is. And it's totally not this bloated beast of a thing that's supposed to have done everything for everyone at all times. That's our entire thing. FM mod algo. You should have seen the wave folding algo. I have absolutely no idea what the wave folding algorithm is doing. This is an FM algorithm. We're trying to figure out what a VCO is doing in code, and we were given code by Hagiwo. This is for Yatemi, who would like to be up to speed, which is nice. It's nice to have people chatting. We've been doing pure math. It's pure math. I hate it. I don't enjoy doing math. We do it if we need to, but I'm so far out of college that I don't remember anything anymore. But so we're doing a bunch of math, and what I'm trying to do is I'm pulling nomials out of a polynomial so that we can put it into code, and when I read the code back again, I can go, what? And then I would eventually understand exactly what's going on. That's not exactly happening right now because there's some nuance to this code. Oops, sorry. There's some nuance to, this is the wrong scene. There's some nuance to this code, and what we're doing is we're producing, basically we're taking a microcontroller and modulating a pulse width modulated output in order to create audio signals. So in one of the modulation schemes, and that's not this one, you can see that the PWM signal is essentially playing a game of Flappy Bird against, oops, that PWM signal right there is playing a game of Flappy Bird against the voltage level of our waveform. And so as we frequency modulate that, as we lower the amount of energy, it goes down, and as we bring up the amount of energy, it goes up, right? It goes up and down and up and down. And we use that in order to create a waveform using all of these equations. And then we control that very quickly by controlling the number of ticks of the PWM signal. We can also amplitude modulate. We can also wavefold. I have no idea what wavefold is, and we tried to find an explanation of it, and we kind of gave up. But the wavefolding happens in a different part of the program, and it involves some other different types of signals. We've looked up how wavefolding works. It has something to do with the triangle wave, but again, it's just not coming through to me. The wavefold modulation has a couple different rules based on the 0 to 256, and it's doing some weird stuff with our mod variable that's calculated elsewhere. I think if given the time and I break out a lot of this stuff and simplify it, I think I'll have a good piece of software going, but The VCO value is being modulated by the low frequency oscillator, amp or mod. The VCO's only task is 1 volt per octave output a waveform. Later on, I believe we're going to go into concepts of, what do you call it, chord VCO and stuff like that. And I'm very interested to see what Hagiwo's code looks like on that. Hagiwo makes a bunch of very cheap modular synthesizer things. I wanted to program this thing in Arduino, and his code was not like clean, but Hagiwo has an amazing channel. He does a lot of really cool stuff, and he's got all these different designs on it, and it's fun to kind of go through and figure everything out about it. What's up, Carabos? So what we've done is I've actually made my own circuit board based on Mutable Instruments hardware design and Hagiwo's circuit. So rather than a $9 VCO, I have something like a $20 VCO, or a 30 or 40. It depends on how exactly I want to calculate my costs. So this is going to be a very good circuit board. We've done all the bodge wire jobs and stuff in order to get this thing to output a waveform. In addition to that, later in time, I can actually use the RP2040 and do some advanced stuff, like look at an audio input waveform and do a filter or something like that. The knobs don't do anything at the moment. All it's doing is serial printouts to the desktop. And the function of that was to make sure that my circuit board was all completely and fully built. Now we've got only the dirty business to do of figuring out how exactly the software is working, and it has quite a lot of nuance to it. It was programmed in Japanese. It was programmed hastily because Hagiwo was just putting modules out left and right, right? It's got a very active YouTube channel. So we're getting into the download nitty-gritty of actually putting together a piece of hardware based on it, and I would have had quite a few of these things. The next time I feel like spending $70, I will order the up-to-date circuit boards that actually work, but for now I have 20 of these things that need somewhat significant modification in order to function. I will correct that, and I'll probably have to throw out the old ones just so I never have the unfunctioning board. Space folding faster than light. Yeah, let's just do the laws of physics, a dirty one there. So we're trying to bend a waveform. We don't really know what folding waveforms does, but we're trying to get to the bottom of the frequency modulation, and the frequency modulation works with these nested sine functions. In order to turn this into programming, I think what I need to do is figure out how I can make something cancel everything following at a certain point. I don't really know how I can do that, canceling out a sine wave function. You could do that with default values, but 2 pi something over something would have to equal what? What is sine of 1? I always forget these basic math concepts. I'm going to take out the calculator here. Do I not even have a sine function in the? Where's my scientific calculator? Sine of, no, I don't want sine of that number. Clear. Sine of 1. I think the sine of 1 is 1, right? 0.17. Are we in radians? Is this sine of 0? This little trigonometry pull down. Sine of 0, 0. That'd be sine of what? Pi? Nope. I know, Wolfram Alpha, I should probably use. I used to be really good with my trigonometry stuff because that played a lot into like control systems and robotics stuff, because you'd be working with them, you know, exponentials and sines and stuff almost constantly. I don't know why I have such a mental block with them though. I think it's just, you know, as soon as the streaming starts, you guys can probably hear Willow barking in the background if you listen very carefully. My corgi is barking at something. What could she possibly see? It's probably the package that they keep saying was getting delivered further and further out into the afternoon. They're like, it'll be there by 10:30. I'm like, cool, 10:30 in the morning, that's perfect. Like, I can go get it, and I can bring it down here, and oh, look, there's my stuff, and we can start stream with the cool stuff that just arrived. Now, then they bumped it up to 1:30, and now 2:30, whatever. Was I able to get the VCO functional? Yes, we're in the nitty-gritty of it, but we were able to actually get, and that's what this thing is outputting right now. It's outputting a pulse width modulated signal that's essentially playing Flappy Bird with our voltage level. And this is the opposite. So you have to think of the waveform as being the opposite of what it is, because it's going through an inverting amplifier. But right now it is doing the I think the frequency, yeah, this is the frequency modulation. So as the frequency becomes more negative, the waveform becomes more positive, and vice versa. Wavefolding doesn't clip, it mirrors the waveform on the y-axis when the input goes above a value. Okay. I don't know what that means. I think that's what all that counting is doing. I just don't understand a lot of this, because this is the part where I am actually getting my, I'm wading into the waters up to my ankles. I'm wading into the waters of this code up to my ankles, and I don't know what I'm getting into. But what I'm trying to do right now is just take an approach of polynomials that could go into a function. So I could have a function that you call that has a certain number of numbers in it, and anything that's missing will default to nothing, and it won't affect the waveform at all. So these are essentially added together, but they're also, well, if each individual piece is added together, then it should multiply out to 0. So I may have to implement control of this waveform by zeroing out stuff like that, because mod 1 over 128, and if that becomes 0, it's 0 times 1 over 128, and that becomes 0, and then sine becomes 0, and this whole additional piece becomes 0. The problem is it blows away everything after it, because these are nested. But I think that's how this works. I think it's supposed to do that. Yeah, so much easier to see it on an oscilloscope. When I see it on, like, if I implement wavefolding and I take a look at it on the oscope, I'll probably see it a little bit more clearly, because you'll see that threshold move up and down, and you'll see the waves folding in on themselves. I think I know what we're talking about. It's just that the implementation of it is beyond my understanding in code. Like, this one blows it away after here, and all that's left is what's outside of the parentheses. This one has this coefficient and then blows it away after here. So if I zero out the nomials of this polynomial, like, I never zero this one out, but I will zero this one out and beyond, and it'll clear it out until the end. So I basically need different mod variables for each set of things. And the mod number changes if I set it as default to -1 and then never call it. But then what about these all the way out here? I guess these would also cancel out if I set, no, the first mod is here, and I'd need to somehow cancel out this. So this would need a variable in front of it. This would need variable sign. So then this would be like mod killer or nomial killer. G G times 4 kill. Nomial. For kill gnome. So if I kill that gnome, I set that to 0, and then that zeroes this out, and then we're adding a 0 to everything. A jump function. I don't know. I mean, how else could you assemble this so that it's a little bit more compact? The way that I'm thinking about it is this whole equation is just in one big function, and you would run the function with all the variables passed into it, and it would kick back the value. So you do all this stuff, and that would give you the mod wavetable of I, and you just call that again and again and again and again, because those variables, the I variable changes from 0 to 256. That I variable changes from 0 to 256 as you go through. And then as you call the function, all of the different variations in the function will be handled by the A, B, C's, and D's. So this one would kill, so it'd be mod C, mod B, mod A. The problem is mod A, B, C, and D are the same number. So it would actually stand to reason if I just put a kill function in each of these. It'd be like kill D, kill A, kill B. That's so weird though. So mod over 128, and then we have sine 2A blah blah blah, and then it would be kill B. And then right here, kill C. Kill D. Oh, but that doesn't kill this, does it? Well, if kill D is activated, then I would have to have it also hit that as well. And then it would be sine, well, then it would be sine of 0, and it would be multiplied by, wait a minute, this doesn't make any sense. Hold on a sec. Well, no, but if I kill C, I'm killing it out here. It would be more like this would kill, but then sine of 2IC is C1. I've got to work this out. It would have to, this would have to be 0, and then it would be plus 0. And then this one would be plus 0, but you would have all the other ones in there. Yeah, that's how it works. So kill B, C, D, and then we do like kill EF. Kill EF. Because then that would default to 0. What about wave folding? Yeah, you can recommend a video about wave folding. Put it in the Discord. I would appreciate that, because I'll check that out later and see if I can watch it and see what's going on. I'm gonna hit save on this document just so I don't lose all this work. I'm sure amplitude modulation is much simpler since it's just one equation. Let me just look at the code for amplitude modulation real quick. You say it's super simple, but when it comes down to the code, it's like a nightmare. And this is Hagiwo's code that we're looking at, by the way. I just took all of these mod wavetables under the individual mode number in the FM mode, and I put them all into one big block to try to understand what the hell's going on. Code looks hard. Okay, well, yeah, hopefully it'll... So what is this one? This is amplitude modulation. If the timer plus the mod is less than or equal to the number of microseconds, add 1 to k. If k is greater than 63, k is equal to 0. AM mod is equal to sine 2 times pi times k over 63. So that just makes a sine wave. Okay, if int I is equal to 0, and if int I starting from 0 to 255 then we set mod 2 wavetable equal to the value of I, which is 2 pi m. Oh no, wait, the value of, so wavetable of 0 to 256. So original wavetable that we create, 0 to 256, and then we multiply it by this godforsaken fucking equation, which is a scale of 63, 2 pi k 63, and k goes from 0 to 63. Every time we run this, we plus k. That's if we expire from a timer. So each time increment, we are adding to k. We are stepping k through 2 pi, the range of 0 to 1 on a sine wave with 63 elements to it. So 63 over our time designation. And then this is me in real time figuring out how software works, by the way, with the gift of being able to just talk about whatever the fuck I'm thinking about. That's what you guys get right now. I hope this is interesting. So our second wavetable, the one that we're actually outputting based on 0 to 256, is coming from our initial wavetable. What did our initial... We made a special wavetable for amplitude modulation. I think we might do it every single cycle, too, which is ridiculous and something that I am going to unprogram. So this one's fold, this one's AM. 1023 minus the value of the pot and this control voltage input from 0 to 1024. I've got to redo that logic. That logic makes no sense at all whatsoever. Because instead of the potentiometer adjusting your control voltage positive and negative 1024, it's taking your control voltage, which defaults to 500 something when you unplug the cable, because that's the way that the electronics work. You unplug the cable, it's got 500 in there. You can't go down from that 500. That 500 is where you're starting. 512 is where you start. And so you could add to it with the second knob. That doesn't make any sense. It should center the two knobs on a number line and then scale that from 0 to 1024. So I'll have to change that. I have to change how all three of these inputs work in order to make them work, because it doesn't make any damn sense. So anyway, back over to here. So we've got a 0 to 1024 in that. Oh wait, we're not here, we're here. We've got a 0 to 1024 as that wavetable of I, based on the original wavetable, which is a scaling of a resolution. My brain hurts. Using digital in an analog system corrects a lot of the voltage errors. Still using the variations of the voltage. Digimods into analog. Yeah, what they're doing here is they're using modulation schemes in order to create a table of values that the microcontroller can very quickly go through. There's a couple things about how the code works that aren't very fast. If you have a table in a microcontroller, you just reference that table for everything you need to know. That's essentially what it's trying to do. It's just that every loop, it's checking the mode and making a new wavetable, which is ridiculous, but it somehow works. We set our timer equal to micros on our exit of this function. If timer plus mod, wait, okay, so that's just using time in order to create frequency based on the values of the wavetable. So there's some weird math going on in here that I don't understand. But this is a clean enough function that I would almost just take this directly. Super weird, but dope. What I don't agree with is that this should be a change state. Like, not this, the one before it should be a change state. So the one before it is where we're reading all of our inputs, like mod parameter set and stuff like that. Mode select is running every single time. If this is that, then set the mode to here. We should have stuff that looks to see if something changes. I think K makes your low frequency sine wave that you're then multiplying by your faster sine wave. There's a whole bunch of stuff with shifting on tables that's going on here that there's a lot of that math that just kind of makes your brain like fold in on itself. And you know, I was hoping that we would be able to figure out little pieces of this code and put it into the synthesizer and then run the different pieces of this code. But it looks like I need to do like a deeper rewrite of all this stuff and figure out how I can kind of speed things up. Because for me, when I'm programming a microcontroller like this, I don't like to have it repeat stuff that it doesn't have to. And it seems like that was kind of left by the wayside. And I respect that completely, that kind of programming, that kind of like, let's just get it running. Let's just get it running. Let's do this. I can't think like that. That's not how I need to mull over every single facet of the program and make sure that things are like, oh, that's not as efficient as it could be. I could move that out there and move that in there. I do that to a degree. I don't do that as badly as maybe some of the chatters with their weird functions that boil down 16 lines of my code into one line. I can't do that. But my understanding of microcontrollers begins with the Arduino, and the Arduino, you have one thread and you got to make the best of it. And so if you're coming through and a mode button is changed, that's a nice time to just go, oh, mode has changed. So while I flash the LED, we'll just calculate the table and then we'll reference the table from then on. But there's also an element of this where things are changing constantly. It's a voltage controlled oscillator. And if you send a signal into it, even from, you know, it's supposed to be able to respond to a wave, like an audio waveform even. Because there's talk about modulating by putting a audio waveform into your VCO, and that way, as the audio waveform changes, you'll have some weird shit happen. You're basically frequency modulating based on your audio coming in. So there's some weird stuff that you can do with synthesizers that we have to like consider, and also our analog voltage levels aren't going to be as stable as they potentially could be. Well, I could put a Cayman filter on those. I've done this famously in the past. That I love my Cayman filters. There's a nice old, I think it's depreciated, library that's a Cayman filter library, and you can just throw it on human interaction stuff so that your joystick will stay centered if you're centered, and if you move it just slightly, it won't move until there's enough of the threshold to kind of break off and move a little bit, and then it kind of filters and smooths the rough input. That's what Cayman filters are all about. I loved the, I forget what it was now. There was, oh yeah, 3D printers. We were looking up 3D printers and optically measuring the height of the carriage. I would still love to do that. Nobody's really implemented anything, and we ran into a thread where somebody was talking about, yeah, but those optical sensors have tons of noise in them. And they're like, whoa, okay, maybe you could have an AI figure out what the smoothed value is of that sensor input. And it's like, this is Dunning-Kruger in action here. You guys don't know enough about anything to know anything. You don't know that you're dumb. When you have bad sensor input, there is a control systems function, Cayman filtering, that you can apply to that input. You can have a very dirty sensor and have an actual pretty smooth, nice output. And that's something that you can implement digitally in a couple lines of code. It takes doing some matrix algebra, which is why I like the Cayman filter Arduino library, the one that's well old and dead. You have to go to the Wayback Machine to get it. But that's really good at filtering controller inputs. You use digital racks like Reactor, aka digital analog to VCO sensors. I have no idea. This is what I have. Oops. Okay, hold on. This is what I have. I have my buddy's old racks and 3D printed front panels on modules that I built from circuit boards. So I built these things up from circuit boards for the sole reason that what happens is when somebody makes a product for a little while, they decide, you know, I'm going to sell something different now and maybe depreciate this one, but I want the communities to still have access to it. So they allow people to remake their circuit boards. And so you can just go to a modular synthesizer shop and just buy a circuit board without even a kit, which I loved. And the philosophy behind it is good luck, asshole, have fun. And that's it. And I'm like, I love that. You're not supposed to contact the people that build the modules because they're done with it. They're done with it. They don't want to mess with everybody's troubleshooting problems anymore, right? And so you get the circuit board and you're like, what parts do I need? You got to look up the circuit board, find like a blog, find somebody else who's worked on it, or just find the design files. In the case of Beautiful Instruments, all the design files are out there. And I've got Fusion 360, so they're compatible. That's what Emilie was designing. Emilie, damn it, was designing everything in. So I have like comprehensive design notes on the thing, and it was down to me to figure out how to build it. Of course, I contacted a YouTuber when I was at my dire straits, and he sort of helped me rubber duck some of my problems, and I ended up figuring out that it was a whole bunch of bad solder joints that were plaguing me, because that stuff was the smallest size of surface mount. I'm using slightly larger SOIC size stuff in order to produce this board. And I'm hoping that this will be a very, very good, I act like I'm actually adjusting something. I hope this will be a very good, more universal board for my purposes. The second one that we have is a chord VCO, but it also doesn't have to be a chord VCO. This one instead has 3 knobs and 1 switch and a button. So I have a feeling this one's going to be a little bit more versatile. But we need to make sure that it outputs everything the way it should. I think aside from some component value changes in order to make things a little smoother, I don't think there's going to be much editing that could potentially go on in this circuit. I think we've pretty much reached the final form, and the design is pretty much at a state where I think it's going to work properly. I will not fully trust that until we do the slight modifications to this board and build it up. But again, I'm getting through the code. I think we've made a lot of progress today just in organizing the math, and I now have a system by which I can activate and deactivate polynomials inside of the system. I'll have to figure out how I can zero out some of the pieces of the function properly. I mean, I could just progressively calculate it from the middle out, but then I would have to store the variable as something, so, oh my god, who knows? Actually, the number of rounds, no, that doesn't make any sense. Number of rounds, and then, because it's got different scaling numbers for all the different polynomial elements, because it does seem like it's like standard form, and then you put that standard form into something that has a standard form, and you do it again and again and again. It feels like doing rounds in like encryption. Yeah, mutables are good. I haven't had much seat time actually producing music with any of this stuff. As far as I can do right now, I can use marbles and basics, and I can get a marching drum beat, but I don't have any filters, and I only have that one 3340 VCO. Crimes and ornamentation pretty much collects dust. There's a cloud sitting down there. Maybe I could do something with that. And then the rest of it is those 2 analog VCOs that don't work, that I've had a lot of analog trouble with. Yeah, they don't work with them anymore, and if you're programming it yourself, you better have some pretty good experience with STM32, which I do now. But you know, it's one of those things, like, in my mind, a project is not worth doing unless it scares you just a little bit. And those mutable instruments circuits were certainly scary. The microcontroller is depreciated, so you have to buy one for like $15. It's crazy town. It's Friday. My voice is starting to go. I think I'm going to leave it here because I need to sit down with the Arduino and program it out. What are the STM32 analog VCOs? I don't know about that. The one that I had, I don't have Fusion 360 open right now, so I won't look at them, but no, those aren't. Oh, the 2 analog VCOs are different. And we did, I think I did a little bit with building it. One of them is a Bic and Tick filter. And the cool thing about the Bic and Tick filter is it's built for the larger rack size. So I took it over the side and broke the PCB. I just broke the PCB in half and then mounted it to the 3D print offset and have wires connecting everything to everything else. I think what I need to do is take that, undo it a little bit, and maybe rebuild it with magnet wire so that it's a little bit more compact wire. And then maybe I can work with it a little bit more easily. What I did is I took a picture of the 2 circuit boards and I drew a red line where the crack was. And so I had that up in front of me and I was able to go point-to-point soldering with the whole thing. That was designed to be like a hardware project that we could work on. I'm still having trouble with it, and it's the same type of oscillator in both of those analog circuits, and it's not working. And I don't know why. So that's something that we can look at later, I guess. I don't know, whatever. Is anybody else online that's not playing Dragon's DLC 2? Can I look at that and see if anybody's worth rating? Flatulent Gonad was on like in the middle of the morning. There's like 5 streamers on right now. Why does everybody hate Friday? Friday's like a nice day to relax and like organize stuff. Or go to work if you do that. Dragon's Dogma 2. Dogma 2. Oh, there's where all my viewers are. I get a lot of viewers from Rabaz because we're buds. All right, I'm shuttering it. I'm putting the stream away. I'm gonna put the stream away. I'm gonna put it in a box so it doesn't collect dust. Yeah, there's Haystack to verify my claims. I don't know. Maybe the Rabaz viewers don't appreciate just doing math, huh? They don't appreciate just pure, the pure love of getting some numbers and then drawing a rocket ship and then flying up to the upper part of the page. From your rocket ship, you take your rocket ship up and you fly up, and then it goes off course because it's fucking SpaceX control systems, and then you're up here and there's another rocket ship that shoots you. Yeah, people don't appreciate that. I'm gonna go look that up on the internet. I'm gonna look up rocket ships shooting rocket ships, just like the one that I'm gonna use Google Images. I'm gonna look this up. I'm gonna look for them shooting each other because that'll be cool. Here's my social media. Math is fun. Listen, I appreciate math when it's not stupid math. Like stupid math is like test math, where they're trying to get you to know all of the little weird rules that apply to stuff. I like math in application, as in this kind of stuff. We're applying math to the meat world, the world of meat space. I like math like that. This is kind of getting into like algebra and functions and stuff that we don't understand because we have to reverse engineer something to a degree. So there's push and pull on that whole thing. But anyway, I hope you guys had fun, all 12 of you that watched me today. And on Tuesday, we will be doing something more interesting, I promise. We'll work on Burn the Subs. And then we'll have lasers that we can turn on and off and do that kind of fun stuff. I used meat space in a meeting the other day and got some funny looks. I heard that a while ago and I forget where. I don't know where I got meat space from. I think it was probably just like an orgy or something. But no, some programmer, and I think it's not uncommon that we call space meat.